Hello NEET warriors, welcome to the next Super 6 class of your class 11 standard topic, which is nothing but waves. So after a wonderful session of simple harmonic motion and oscillations, I hope you have watched it. If you're not, please watch it. This session is the next follow-up class, because if you do not understand SHM, it might be a little bit tricky at the beginning. So my advice is, please make sure you have watched SHM. This is a very important chapter, very straightforward and simple questions do come in NEET. So if you are targeting 700 plus in the NEET examination, you must complete this waves chapter. So there are two major things in this. One is wave on a string. The second one is sound waves. Both the concepts are there in this particular chapter. Also, it lays the foundation for your class 12th topic, which is light waves. Okay, so let's begin with this class, and this is your Captain Shreyas. Nice to see all of you. Hello Sarat, Suha, Krishna, Ajay, Yashwan, Niriksha, Omna, welcome Dipanvita, hello Shirwal, hello Darshika, hello Zuha, hello Sweta Prasad, hello Ajay, hello Sanvi. All our regular students plus the new students are here, and make sure you are marking your attendance by smashing the like button. And if you are new to the channel, welcome to Vedantu NEET English, the top-notch English channel in the country for your NEET preparation. We started for all the South Indian students because there were many Hindi channels, but English channels, we are the first ones to do it. So the biggest channel in the country. Not just that, now we have so many students across the borders throughout India watching these classes. Thanks to all of you. Let's make this channel great. So thank you for subscribing and thank you for loving. And my name is Captain Shreyas. I have done my BTech from NIT Nagpur, research from IIT Bombay, and sending the kids in the top-notch colleges in the country. So that's my quick intro. So let's begin with the lecture, and that is waves. Now when we say waves, first thing that comes to your mind is sea waves. How many of you thought sea waves? How many of you thought sea waves? Yashwan, there is going to be a surprise tonight. That's the reason why I have not shared the schedule. There is going to be a big surprise for the entire week. We are going to come up with a challenge for the next 5 days, and I'm pretty sure you will be ready for it. So wait for it. Tonight I'll be letting you know what the challenge is. So my dear students, yes, you thought about sea wave. Sea wave, yep. Then guitar strings or a sitar or any string instrument, you pluck the string, that there is a wave which is formed on the string instrument, or you play a flute, right? And if you hear some sound from the speaker or a guitar or a harmonium or a piano or drums, the sound is traveling via sound waves. Or you might have used spring toys. You take a spring and you elongate it, you will see something goes back and forth. Some wave-like structure goes back and forth. You might have also heard about light traveling from the sun to the earth in the form of electromagnetic wave, which is light. So light travels in the form of an electromagnetic wave. All these are examples of waves. It tells you waves are there everywhere around us, be it musical instruments, be it even an earthquake, be it a sea wave, be it the sound that you hear from speakers, be it a toy, or be it the phenomena of the light reaching the earth from the sun. All these are waves. Yes, is that right? Perfect. But then the real question is, what exactly is a wave? How do I know it is a wave? And is there something opposite of a wave? How many of you know there is an opposite of a wave? What's the opposite of a wave? Let's see how many of you are able to think it and write down in the chat box. If you are watching it recorded, still you can just say it in your mind and see if your answer matched with any of our students or with me. So let me give a very straightforward example, my dear warriors. What is the difference between a wave and a the opposite of it? So what happened is, one day Pandu was standing in a line. All right, and there were many Pandus in front of him. Many Pandus in front of him. Pandu was trying to book a ticket to go out with Champa, movie ticket. So these are all Pandus in the line. This Pandu is also waiting, but this Pandu wants to go out with Champa for a movie. So he's standing in a line for buying the movie ticket. Now, there are two options for Pandu to, overthrow these people, overthrow these other Pandus, and make sure that he ends up getting those tickets faster, or other people are injured or they are out of his way. What are those two ways, you might ask? Well, one way is what Pandu does. He picks up this Pandu. He takes this Pandu and throws this Pandu on this guy's head. Understood? What does he do? He takes this Pandu and throws this Pandu on this guy's head, because this guy was taking a lot of time maybe. It's very irritating. Sometimes happens when you are standing in a line, one person unnecessarily wasting time. Card is not working, change is not there, this is not working, asking should we do this or should we do that. Has it happened to you? You are standing in a line and the person in front is irritating the hell out of you. Something like that only is happening. Yes? So this Pandu lifts the other Pandu in front of him, throws that other Pandu. So this Pandu gets knocked out. Dhup karke he will fall off. Right? So now that he is injured, these next Pandus are very eager. Tuck, they will book the tickets, and this Pandu will be able to book the movie ticket for Champa. Understood? This is one way. Very good. Second way is, what this Pandu does, he does not lift this Pandu. He will just push this Pandu. So this Pandu falls on this Pandu falls on this Pandu falls on this on this, this on this, this on this, this on this, and this Pandu falls down. Once this Pandu falls down, then this next person buys the movie ticket. In both the cases, the Pandu in the front fell down. In both the cases, be it this one or in this one, the Pandu in the front fell down. The Pandu in the front got some energy, yes or no? Very good. So, the Pandu got some energy from whom? This Pandu over here. From this particular Pandu over here. So, I can call this as the source. He's the source of energy. This person is the receiver, or I would just say the destination, alright, or the destination of that energy. Destination of that particular energy. Where did it go? Yes. Destination of that energy. I can also say the energy is traveling in this direction. Energy is traveling in this direction. I can say that the energy went from the source to the destination in this particular direction, but the mode of energy transfer was different. In the first case, the particle, and in this case the particle was this Pandu, the particle, or I would say an object, was the carrier of energy, right? The particle then itself went, the body itself went from point A, that is the source, to point B, which is the destination. Okay, the particle itself carried. It's like, okay, I will take this and I will go. That is one way. That mode is called as the particle mode, and that is the opposite of a wave basically. So that is called as the particle mode of energy transfer. Whereas in this case, particles did not go from one place to the other. This Pandu did not go here, this Pandu did not go here. They were at their own place. They just fell down. Tup karke they will fall down. Yes or no, my dear warriors? So in this case, the particles were at their equilibrium positions, just that they passed the parcel, they passed the energy from one place to the another. So they just passed the energy. This kind of mode is called as a wave mode. This is what? This is called as the wave mode of energy transfer. Is that clearly understood? So now what is the two different ways? One is of energy transfer, one is particle mode, where the particle itself goes from one place to the other. It's like your courier service. The person only takes the courier and goes to the other destination. Another is passing the parcel. You tell your neighbor, hey, listen, tell this message to next person, that next person tells it to the next. All the people are at the same place, they are just transferring the quantity like energy from one place to the other. So wave is a disturbance in a medium that carries energy without net movement of particles. This is what is there in your NCERT also. Does that make sense? Wave is a disturbance. I disturbed that pandu, I pushed, I have disturbed that pandu fell on the next pandu, that next pandu fell on the next pandu. That is also called as the domino effect. You might have heard of Domino's pizza. So domino effect is like, you have one thing, it falls on the next thing, that next thing triggers the next thing triggers the next, and something else only happens towards the end. That is called as the domino effect. Remember Domino's pizza? So that is Domino's effect. Is that clear? So this is basically called as your domino effect. What is this called as, my dear warriors? This is called as your domino effect. Domino effect. How many of you have seen videos of domino effect? How many of you have seen examples of Hello. Yes, I'm there. Yes. So I was saying that, this is called as a domino effect. You can watch the videos also on that. And this is exactly what has been mentioned here. Now, whenever you want to transfer energy from one place to another, there are two critical properties which a medium generally possesses. One is elastic property, second is inertial property. So you can see that elastic property has been mentioned over here, okay, and you will see that there must be also some kind of inertial property as well. Inertial property and obviously elastic property should be present in that particular medium for the wave to propagate. I'll tell you why. What is this elastic and inertial? Inertia means mass. Elastic means tendency to come back to its original shape and size. Elastic means tendency to come back to its original shape and size. Everybody agrees with this? Very good. Now, look at this. When you pluck a guitar string, won't that string again try to come back to its original shape and size? Isn't that so? Even a sea wave, if a wave goes up, it will try to again come back to its original shape and size. If you talk about a spring also, if you compress a spring, it will try to come back to its original shape and size. So that is elastic property. If that was not there, just imagine you elongate a spring, it stays like that. Then why will a wave go? Why will a wave go? It is elongated, it stays like that, nothing will go. So there must be some kind of elastic property. Is that making sense? Second thing is inertial property. Inertia means mass. So how will the energy go? Something should be carrying that energy. In this case, the string's mass is carrying that kinetic energy. The sea is made of water. The water particles are carrying that energy. The spring is made of some steel or some metal. The metal is carrying that kinetic or that energy, whatever is there, from one place to another. Are you able to understand? So that's the reason why I said there must be generally inertial property as well as elastic property in the medium. But there is a catch for elastic property. You don't always need that elastic property. This elastic property is only needed in some kind of waves only. That is basically your mechanical waves. We will talk about it in a bit. But for now, till this point, if everything is clear, then we will go ahead. Very good. So mass is carrying the energy. Exactly. Mass is going to carry the energy. So the mass of the spring, the mass of the water particles, the guitar's strings mass, or when you talk, the sound particle, sound is moving because of the air particles. The air mass is carrying that energy. The mass of the particles of the air, molecules of the air, they are carrying the sound energy. Keep that in mind. Very good. Awesome. Now, like I said, there are multiple ways in which you can classify a wave. Now, one of the classification is called as a mechanical wave. Mechanical means requires a medium. The other one is basically The other one is basically non-mechanical waves. It's basically non-mechanical waves, and the best example of that is basically light or basically any electromagnetic wave. Any electromagnetic wave is a non-mechanical wave, meaning they don't need any medium. They don't need any medium. If a medium is there, okay. If a medium is not there, still okay. Doesn't matter whether it is there or not there, it can still travel. That is a non-mechanical wave. So no medium needed. No medium is needed for it. Now these kind of waves, because they don't need medium, that's why I would say they don't have mass-like property or inertia-like property. Like light can travel in vacuum from sun to the earth, there is nothing in between. Still light is able to travel, means what? There is no need of any medium or particles or mass, no inertia is there, and it is a non-mechanical wave. Example of mechanical waves, everything. Ripples on water, sea waves, earthquake, spring being pulled and released, that springs disturbance traveling, guitar's string plucked, the wave on the string, sound waves, everything needs some medium. Everything needs some medium, correct? So that is mechanical wave. That is mechanical wave. Now this mechanical wave also can be further classified into two categories. One is called as the transverse wave. The other one is called as the longitudinal wave. Transverse, long. Transverse means perpendicular. Long means along something. So what is the meaning of transverse versus longitudinal? Let me explain to you via this example. So if it so happens that a wave is traveling in this direction, this is the direction in which the energy is traveling, or basically I would say the wave is traveling. So this is the motion, this is the direction of the motion of the energy or the wave. Then the particles go perpendicular to it. Then the particles go perpendicular to the direction of the motion. That is called as a transverse wave. Examples will be, what are the best examples? Waves on the water. When the sea waves or the water waves go, you will see the particles go up and down, and the wave is going horizontally. Or you take a string and you generate a wave. The particles of the string go up and down, but the wave goes horizontally. So that is a good example of a transverse wave. Is that clear, my dear warriors? Exactly. So transverse, trans means perpendicular. So transverse, the trans means basically perpendicular. This is long. This is like along the direction. So longitudinal waves, the particles go along the wave. So if the wave is traveling like this, this is the motion of the wave, or basically your energy, motion of the wave or your energy. The particles, do you see the particles? The particles are going along, meaning parallel. They are going parallel, that is along. That is called as a longitudinal wave. Example, when I talk, the particles of sound go back and forth. I am talking, the energy is going, let's say, like this. The particles of sound go like this. The particles of sound go like this. Close and far away, close and far away. That is a longitudinal wave. Is that clear, my dear warriors? Alrighty. So let me show you some creative visualizations which you all must be very, very interested in. Just hold on. Let me just get this. This is a very cool site. And let's go to waves. So you can also try this out later on. Go to ophysics.com, go to waves, okay? And in waves, there are many things. So let's just go to waves tutorial. It is a very interesting simulation. Let's go to this. So do you see, last lecture we had studied oscillation, simple harmonic motion, up and down, left and right, back and forth, repetitive nature, represented by sines and cosine equations. So this is your simple harmonic motion. What if I take many such springs and masses and make them oscillate together? You will see a beautiful wave just like this. Oh my God, look at this. How many of you are able to see a wave going? How many of you are able to see a nice wave which is traveling from one side to the other? Isn't it fascinating? And do you see these particles are going up and down? See, this particle is not going right or left. This particle is just going up and down, up and down. There is elasticity because of the spring. There is mass that is giving inertia. So elastic and inertial, both properties are there. Do you see that? By the way, the upper part, what is that upper part called? The upper part of a transverse wave, that upper part, what is it called? It is called as a crest. The peak is called as a crest. And what is the lower part called? What is that lower part which is going is called? The valley part. The valley part is called as a trough. So it is a crest and a trough. Crest and a trough. Yes, Shivani, nice waves that you have drawn. Great. So beautiful transverse wave. You can see the particles going up and down. But the feeling, that is magical, no? Particles are just going up and down, but you get the feeling that as if something is going here. But nothing is going here apart from energy. Particles are just going up and down. Now similarly, look at this longitudinal wave. Do you see that there is some kind of a thing, disturbance which is going from one side to the other? Like, look at this, compression is going like this. You can see rarefaction is going like this. Compression means they are compressed. That part is called compression. Rarefaction means it is elongated. That elongation is traveling. That is rarefaction. Notice how the energy is going like this. The particles are going back and forth, back and forth, back and forth. So again, inertial and elastic properties both are present in this mechanical wave. And you can see the energy travels in the same direction as the motion of the particles. Hence, it is longitudinal. So what are they called now? Compressions and rarefactions. Compressions and rarefactions. So when we talk, there is a sudden increase in pressure, sudden decrease in pressure, increase in pressure, decrease in pressure, increase, decrease, compression, rarefaction, compression, rarefaction. If you take a tuning fork, you might have seen that in the lab. It looks like this. It has got a handle and it has got two forks like this. You hit it somewhere, ting karke it will vibrate like this. What will it do once it vibrates? It will compress the air and expand the air. Compress the air, expand the air. So there will be a compression, rarefaction, sound wave which is traveling in the air around you. Exactly. Very good. Amazing. Yes, Krishna. Great. So in the next page also there are many amazing things which we will be seeing over here, and that is basically related to the amplitude and also the frequency and all of that, because those are the next parameters that we have to see after that. Okay, so let's talk about wavelength, displacement, amplitude, frequency and velocity. Let's learn that. Most of you know all these things, but I feel you should visualize it, you should feel it, you should creatively imagine it. If you are able to imagine, feel and absorb it, that's the best way to learn physics. Look at this. This one over here is a longitudinal wave. You can see that this is longitudinal. The blue one is a wave on a string like thing. So it is a transverse wave. Okay. Do you see the particles are very close here? Compression. Particles are very far here? Rarefaction. Compression, rarefaction, compression, rarefaction. Peak is called crest, valley is called trough. Peak, valley, crest, trough, crest, trough, crest, trough. Great. From one compression to the next compression, or from one crest to the next crest, that distance is called as the wavelength. Okay? One crest to the next crest. Okay, or one compression to the next compression is called as the wavelength. So can I also say wavelength is from one rarefaction to the next rarefaction, or from one trough to the next trough? Yes or no? Will this distance from one crest to the next crest be the same as one trough to the next trough? Yes or no? Yes, it will be. Also, from here to here, compression to compression or rarefaction to rarefaction, it's going to be the same thing. Yes or no? So it doesn't matter as long as you are getting similar things. That is called as your wavelength. Very good, very good, very good. Amazing, amazing. Everybody is able to see that. Right. Now, what is amplitude? Amplitude decides how tall this wave is or how much are the variations. Look at it. I will reduce the amplitude. I'll reduce the amplitude. See how this wave became thin. It became thin. So it is not going up and down so much. It's not going up and down so much. Look at this. It's compressed, rarefied, but not so much. The variations are less. But the moment you increase the amplitude, more rarefaction, more compression. Taller and deeper. Higher crest and lower trough. Right? I increase the amplitude even more. Look at it. It got more compressed, more rarefied. Higher crest and lower trough. That is the meaning of increasing the amplitude. Right? So let's run these waves and see how it goes. Let's run this. See how beautifully the waves are going, be it longitudinal or be it transverse. See how the wavelength is going like that. What will happen if I change the frequency? When I change the frequency, I'm making it go up and down fast or left and right very fast. So let's change the frequency. Oh my God, look at it. Look at it. It's, I think, going slightly faster. Do you see that? It's going up and down faster. So it is also going little bit faster. If I reduce the frequency, I think it is now going little bit slowly. Yeah, such a nice simulation, guys. Such a nice simulation. After this, we will be completing this lesson today only. We'll be completing this lesson today. So these are some interesting things which you should know about waves, be it amplitude, frequency, wavelength, etc. So wavelength is nothing but the distance from crest to crest or compression to compression or rarefaction to rarefaction or trough to trough. That is understood. Okay, that is denoted by the symbol lambda. That is denoted by the symbol lambda. Amplitude A is nothing but the maximum displacement from its equilibrium. Now what is this displacement? This could be represented by a symbol Y. It's the displacement from or displacement of a particle, from its equilibrium. This is maximum displacement. This is just the displacement. Understand the difference. So this is amplitude. This whole thing, observe, this whole thing is amplitude. But at this point, it is not maximum. So this is the current displacement. This is maximum. This is some displacement, zero displacement, negative displacement, negative, zero, positive, amplitude. So displacement is some instant, anything it could be, zero, positive, negative. Amplitude is always positive. It is a maximum displacement that you can undergo. That is the difference between it. Is that clear? Okay. Frequency, the symbol is F. It is the rate of the disturbance, right? That means how many waves are going per unit time. It's also basically number of waves per unit time. V is nothing but the velocity of the wave, the velocity of the wave, which is also the speed of energy propagation, the speed of energy propagation or transportation, how fast it is going, transportation. Are these related to each other? Definitely. Definitely they are related to each other. Definitely they are related to each other. So if this is our equilibrium, and I tell that, listen, this is our wave, something like this. This would be obviously your amplitude. This, at some point, there will be some displacement. This is y. This is the x position, maybe. Let's say this is origin. So I can just say this is basically your x and this is basically, let's say, your y. Y can keep changing. A is, remember, the maximum displacement from here to here, correct? And let's say this was your origin. So this is your y-axis, this is your x-axis, and then from here to here is one wavelength. I'll write it like that. And since the wave is going to go like this, with some speed v, that v is f into lambda. Keep this in mind. This is a standard equation. Everybody should know this. Wave speed is the frequency into the wavelength. Wave speed is the frequency into the wavelength. Very good. Yes. Not just that, you should also know one more thing, that is frequency is 1 by time period. What is this? What is this time period? This is the time it takes to go up and down. This is nothing but your time period. This is nothing but a time period of the oscillations of the particles. Time period of the oscillations of the particles. This is the formula for your wave speed. This is the formula for your wave speed. Keep this in mind. All right. And since these particles are going up and down like oscillations, SHM, can I also introduce this term omega? Do you remember omega? Omega was 2 pi by time period, which is also 2 pi f. This is also valid over here. This is also valid over here. This one is just called angular frequency. Angular frequency. Not just frequency. Angular frequency is 2 pi f or 2 pi by t, which is omega. Same omega which you have used in simple harmonic motion. No difference at all. Yes. Thank you, Suraj. Limitation King will be probably doing gravitation, okay, after this, right? Because that was also on demand. All right, great. So keep all these things in mind. Keep all these things in mind. Okay, these are very, very important. Apart from that, there must be one more parameter which you should know. If you have a wave like this, and I know that from here to here is wavelength. This is nothing but your wavelength. We define one more parameter called as the angular, just like this was angular frequency, which was, always measured in radians covered per second. There is angular wave number. This is expressed in radians per meter. The symbol for that is K, and the formula is 2 pi by lambda. 2 pi by lambda. This is angular wave number. K, which is 2 pi divided by lambda. Let me give you an example. Imagine if I tell you the wavelength of something is 4 meters. Then what will be the value of the K? The value of the K will be 2 pi divided by lambda, which means 2 pi divided by 4, which is pi by 2 radians per meter. let's understand this. Let's understand this phenomena. What is this pi by 2 radians per meter? See, if I have my wave like this, okay, when I say pi by 2 radians per meter and the wavelength itself is 4 meters, the wavelength itself is 4 meters. This is basically your 4 meters. Then understand, if I take 1 meter, I am seeing pi by 2 radians. Actually, 2 pi radians is one oscillation. 2 pi radians is one oscillation. Just think about it. If you remember correctly, 2 pi radians always used to correspond to one oscillation. So pi by 2 radians, isn't it 1/4 of an oscillation? 1/4 of an oscillation. 1/4 of an oscillation. Similarly, 2 pi radians will be one wave. So pi by 2 radians will be 1/4 of a wave. 1/4 of a wave. So when you go up, down and come back, it's one wave, one oscillation, that is 2 pi radians. So a part of it, my dear students, will be nothing but 1 meter is 1/4 of the complete wave. This much, this much, this much, this much. It's 1/4 of the complete wave. So that's the meaning of it. Pi by 2 radians per meter means if you go 1 meter, pi by 2 radians oscillation wise, angle wise, phase wise is covered. That is the true meaning of it. That is the true meaning of it. Okay. So don't think, sir, pi by 2 means 90 degrees. So what is going in 90 degree? No, no, no. Nothing is going in 90 degree. It's telling you one oscillation, one wave is 360 degree. So 90 degrees is 1/4 of the complete wave. So 1/4 of a wave is there per meter. That is the meaning of it. Similarly, my dear warriors, if I tell you the value of K is 6 pi radian per meter, meaning what? Meaning what? Think about it. In 1 meter, there are 6 pi radians. 6 pi radians is 2 pi into 3 radians per meter. 2 pi radians is basically one wave. So like that, there are 3 waves in 1 meter. So my dear students, if you draw 1 meter, how many waves are there in it? If you draw 1 meter, how many waves are there in it? 3 waves are there in it. 3 waves are there in it. This would be the wavelength, obviously. This would be the wavelength, but this much is 1 meter. This much is 1 meter. In that 1 meter, 1, 2 and 3. 3 waves are there. That is the meaning of it. Are you now getting a feel of this value of K? Are you now getting a feel of this value of K, my dear students? So now that we have discussed what is K, everybody knows what is frequency also. Frequency is measured in hertz, obviously. We know this from before, from the chapter of oscillations. Hertz is 1/second. And we have seen what is wavelength, displacement, amplitude, frequency, velocity, and even this formula. Now, let's do some questions which are going to come up on your screen. We are going to complete NCERT plus PYQs. So we get a complete picture both from NCERT as well as NEET point of view, and that is what NTA will or NMC will target. Given below are some examples of wave motion. In each case, if the wave is transverse, longitudinal or both, that's what you need to tell. Okay, option A, motion of a kink in a longitudinal spring produced by displacing one end of the spring sideways. Okay, so kink is a motion of a kink. Basically, kink means a long spring. It's a long spring. If you take a long spring and if you pull this like that, then you will see a transverse wave going like this. You will see a transverse wave going like this, but then the spring also will be elongated, no? The spring also will be elongated in some places and then compressed in some places. It will be elongated in some places and it will be compressed in some places. So a disturbance is traveling not just transverse wise but also compression rarefaction, because when you pull it sideways, you are elongating it, and that elongation will obviously create compressions and rarefactions ahead. So both things are there. Can I say that? Why 1 meter, Deepanvita? Because that is how K has been defined. It is radians per meter. Per unit meter, how many radians are there? Just like angular frequency is the radians per second. So per unit time, how many radians? So per unit meter, how many radians were there? That's why per meter. Okay. Yes, both transverse and longitudinal are there for this. Waves produced in a cylinder containing a liquid by moving its piston back and forth. So if you have a piston inside a cylinder and you take this piston and you move it back and forth, if you move it back and forth, obviously that will create compression rarefaction. Compression rarefaction, which is going to travel, what will it create? What will it create, my dear warriors? Only longitudinal will be created. So here only longitudinal will be created in this particular situation. In the first situation, both longitudinal and transverse were created. The next one, what is it? Waves produced by motorboat sailing in water. What kind of waves will be created? Motorboat sailing in water, my dear warriors. So imagine this is your water. So some ripples are created. So those ripples will travel. So that will be transverse wave. But because that boat is traveling with some nice high speed, don't you see that there will be also some sound which will be created inside the water? The sound which is created in the water, isn't it longitudinal? Sound will travel inside the water, obviously. So that will make it longitudinal also and transverse as well. So that is C. Yes, both are created. A lot of people only think about transverse, forget the longitudinal part. Okay. Ultrasonic waves in air produced by vibrating. Now ultrasonic is basically, it's nothing but sound. It's basically nothing but sound which is heard by bats. So this is nothing but sound, and sound is always longitudinal. Sound is always longitudinal. So that will go in all the things. It is not transverse. So hence it will be only longitudinal. Yes, we have got this correct. Both only longitudinal, both only longitudinal. That is the exact answer what we have written down. Moving to the next one. If a hospital is using ultrasonic scanner, you will see ultrasonic scanners are used in many places to locate tumors in a tissue. The wavelength of the sound in the tissue is how much? If the speed is this much and the frequency of the scanner is 4.2 megahertz. This is a NCERT back exercise question. Yep. Sir, we have to do optional questions for NEET? No, obviously not. Aditya, only you have to do the compulsory questions. You don't have to do everything. Yeah, the optional questions are optional. That's the reason why it is optional, right? So out of those 10 questions, you will only solve those 5 questions. Okay. So how do we solve this, my dear warriors? Think about it. How do we solve this, my dear warriors? Think about it. Here, I can use the formula V is equal to F into lambda. Is the speed known? Yes, it is 1.7 kilometers, means 10 to the power 3 meters per second, is equal to frequency is 4.2 mega, that means 10 to the power 6, this is hertz, into the wavelength. The wavelength will be in meters. So what will be the wavelength? What will be the wavelength? So it will be 1.7, 10 to the power 3, 10 to the power 3 will cancel, divided by 4.2 into 10 to the power 3. That's what I'll get. Shift the decimals. It will be 17 by 42 into 10 to the power minus 3 meters. Do the math and see approximately how much will it come, because I can write it as 170 by 42. So it will become 170 by 42 and this will become 10 to the power minus 4. So 4 4s are 16, 40 into 4 is 160, 42 into 4 will be 168. So close to 4 point something. around, I think 4.1 or something like that it will be. 4.1 into 10 to the power minus 4 meter, approximately I'm saying. Yes, it is 4.1 into 10 to the power minus 4. That's what it will be. Yep, very good. Yes, we'll be having special physics classes for the board examinations also. Just give us some time. Definitely this week you will see what is going to happen with regards to NCERT also and with regards to NEET. And then following up, you will see before your board examinations, there will be long marathons for all of you. Okay, next one coming up on your screen. A bat will emit ultrasonic sound of frequency 1000 kilohertz in air if the sound meets a water surface. What is the wavelength of the reflected sound, the transmitted sound, and all of that? Okay, so there is this water surface. The sound is coming, from air. Okay, it is having some wavelength. It is having some wavelength over here. The speed of the sound in air is 340 meters per second, and the frequency is how much? 1000 kilohertz. 1000 kilohertz. First, can we find the wavelength in air? Definitely. Wavelength is speed by frequency. Speed is 340. Frequency is 1000 into 10 to the power 3. Do you see that, my dear warriors? Kilohertz is mentioned. Kilohertz is mentioned. You need to be very careful. So this 0 cancels. So it will become 34 into 10 to the power minus 5. If you want, you can also write it as 3.4 into 10 to the power minus 4 meter. This is the wavelength in air. This is the wavelength in air. Now, what about the wavelength inside water? What about the wavelength inside water? I know the speed inside water is 1486 meters per second. Will the frequency change or the wavelength change? Answer is frequency will never change even if the medium changes. Whenever the medium changes, speed of the wave changes, frequency never changes. White color remains white color, blue color remains blue color. If somebody is saying, come help me, inside water also it will go as come help me. If somebody is screaming ba karke, it will come out only as ba. If somebody is saying sa, it will go as sa. It will not go as pa. Okay, so this will still be 1000 kilohertz. Frequency is unchanged. Keep this in mind. Always whenever medium changes, it's the frequency which is unchanged. So the wavelength inside water, again, it will be 1486, which is V. Frequency is basically 1000 into 10 to the power 3. So this will become 1.486 into 10 to the power minus 3, which you can also write it as 14.86 into 10 to the power minus 4 meter, so that it is easy to compare. It was 3.4, now it has become 14.86. So the wavelength has clearly changed. Now did you understand these NCERT questions? How many of you are facing? How many of you are facing these issues? Yep, very good. Pavish, Vijay, I think you were late to the session. At the start of the session, I have discussed all these examples of transverse and longitudinal wave. I also showed the simulation part. I hope you were there that time. If you are not, just rewind back a little bit. You will see the examples as well as those simulations. Great. Those are the answers. Moving on now to the displacement relationship in a progressive wave. To the displacement relationship in a progressive wave. What is the meaning of this? Okay, sounds little bit crazy, right? But actually it is not. I'll tell you what I'm referring to over here. Let's say this is our x-axis. Let's say this is our y-axis. This is our origin. Let's say sometime back, our wave was over here like this. And I focus my attention on a particle which was, let's say, over here. Particle which was here at some instant t1. This is at t is equal to t1. This is the particle which is over here. Alright, it is displaced by this much amount. As time progresses, the wave will also go ahead. The wave will also go ahead. All right, maybe the wave will reach here after some time. Something like this. Now, where is the particle going to be? Where is that same particle going to be? It will not be here. In fact, it will be here. This is that same position of that particle at time t is equal to t2. At time t is equal to t2. Do you see that? How many of you are able to see this? After some time, the position of the particle has changed. It will keep going up and down. It will keep traveling differently. At different times, it is at different places. Which means, if I ask you what is the y coordinate of the particle, I will say definitely it is a function of the time. It depends on the time. At which time are you looking at it? At this time it is here. At some other time it is here. At some other time it will be somewhere else. So do you agree it is a function of time? Do you agree it will be dependent on time? Not just that. Also, at the same time, every particle on the string or that wave is at different places. Like, say for example, if you look on that same wave, at the same instant t1, some another particle, let's say I call it particle q, at that same instant, it is at a different y. On the same wave, some another particle, let's say I call it r, it's at a different place. So what also matters is where you are on the x-axis. On the x-axis here, you are here. On the x-axis here, you are here. On the x-axis here, you are here. So your x also matters and time also matters. So can I say it is also dependent on the x coordinate? It is also dependent on the x coordinate, yes or no? Very good. Now, if our y coordinate of any particle depends on two things, you give me x and time, only then I can tell you the y location. This y location is also called as the displacement. Displacement. This is a function. This is a function of your equilibrium position as well as the time. Because if you notice what that x was, what is that equilibrium position? So if the particle was not going up and down, this is where it would be, this is where it would be, this is where it would be on the x-axis, which would be the equilibrium position. So the displacement is a function of equilibrium position and time. But what is that function going to be like? What is it going to look like? That function will always look something like this. Either it will be kx plus or minus omega t, okay, some function, or it could be some function where it is omega t plus or minus kx. Do you remember what was omega? Do you remember what was k? K is angular wave number, omega is angular frequency. It will be some form of kx plus minus omega t or omega t plus minus kx. Now, when to use plus, when to use minus is the interesting thing. First of all, just know for now, this is called as the general wave equation. General wave equation. I will simulate this for you also. Don't worry. I'm going to simulate this for you also. And in this general wave equation, if it is a plus sign either here or here, then it is going, then the wave is moving along negative x-axis. But if it is a minus sign, then it is moving along the positive x-axis. Moving along the positive x-axis. So if it is a plus, it is going like this. If it is a minus sign, it is going like this. Say for example, I tell you y is equal to something like, I don't know, maybe 10 by 4x minus 2t whole square. Tell me over here, what is the value of k and what is the value of omega? What is the value of k and what is the value of omega. K is always with x, omega is always with t. K is always with x, omega is always with t. So look at this equation. Do you see some function, some equation is there, it doesn't matter what nonsense, but x is multiplied with 4, so k is 4, omega is nothing but 2. Omega is nothing but 2. Everybody is able to see that in this particular equation? Similarly, I can give you one more example. Y is equal to something like maybe 4 times cos 3t plus maybe 9x, okay, something like this. If you compare and see what is the value of k and what is the value of omega, k is the coefficient of x, so it is 9. Omega is the coefficient of time, so it is 3. Do you see that? Everybody with me? Great. Now this one has a minus sign. What does this mean? Minus means it is moving along the positive x-axis. So over here I can say the wave is going along the positive x-axis. Positive x-axis. Because there is a plus here, the wave is going along the negative x-axis. If you don't believe me, it's okay. Let's make you believe this. Let's make you believe this, right? So let's go to Desmos graphing calculator. Okay, it's a beautiful calculator. What was my original equation, my dear warriors? What was my original equation? Let's do this. Y was something, right? Y was 10 by 4x minus 2t whole square. Okay, so y was 10 divided by 4x minus 2t. So 4x minus 2t and then whole square. Just see if you can see, it's exactly the same equation what we just did, 4x minus 2t whole square. 4x minus 2t whole square. And the next equation, all right, so 1 second, let me just put some numbers over here, 10 and this is 0.1. Okay, and the next one over here, y is equal to what was this? 4 cos 3t plus 9x. 4 cos 3t plus 9x. So 4, and then we will use the cosine function, and this was nothing but 3t plus 9x, 3, and then we will use t plus 9 and then x. See this. Oops, I think I put the bracket early over here. 3t plus 9x. Okay. Do you see this beautiful? Oh my god, this became way too much. Is it? Okay. No problems. It's just become way too much like this. It's gone high. It's like a big pulse over there. Okay, no issues. Let me just play the time. Where should it go? It should go on the positive x-axis because it is 4x minus 2t. See where it is going. Do you see the wave traveling? How many of you are able to see the wave traveling? Isn't it amazing? One of the best things. First time you are seeing a wave traveling in a graphing calculator, right? Okay, it is coming back. Time should not come back. It should just go here. Yeah. So it should just keep on going like this. I'm taking it only till 10 seconds. So only till 10 seconds I am able to see it. Isn't it amazing? Let's try this cos. Do you see this cos? Let's see what happens. See, it is going towards the left side. I don't know whether you can see it, but yes, it is slowly going towards the left side. How many of you are able to see it? Amazing, right? What a brilliant sight. So now that you have seen this, you realize why, you know, this kind of functions are wave equations. Something t, something x, something t. Plus means negative, minus means positive. Minus means positive, plus means negative, direction of travel. Not just that, you will see one more thing over here, and that is the wave speed. that is the wave speed. So let me tell you, the wave speed, which was also f lambda, can also be written down as omega by k. Omega by k. This also can be written down. There is no harm in this. Some of you will be like, sir, what is the proof of this equation? It's very, very straightforward. Since v is f lambda and we know that omega is 2 pi f, therefore f is omega by 2 pi. Also k is 2 pi by lambda, therefore lambda is 2 pi by k. Substituting it over here, instead of frequency put it as omega by 2 pi, instead of lambda put it as 2 pi by k. 2 pi cancels, you will get it as omega by k. So that's how you get v is omega by k, which is right over here. That means in this particular equation, do I know the wave speed? Definitely. V being omega by k, omega is 2, k is 4, so it is 0.5 meters per second. Do I know the wave speed over here? Yes, again omega by k, that is 3 by 9, which is 1 by 3 meters per second. So you can find the wave speed if you know the equations like this. Understood, everybody? How to play with these equations? Has everybody understood, my dear students? Let me know. Very good. So now, my dear students, my dear warriors, yep, if I write an equation which is a sinusoidal wave equation. What is the meaning of sinusoidal wave? Sinusoidal. See, these waves, this one cos is a sinusoidal. This one is not a sinusoidal. Sinusoidal means it should be up and down like a sine wave. Even a cos is, don't call it cosinusoidal. Don't say such things. Cosinusoidal. Don't, there is no such word as cosinusoidal. Okay, you will get one nice beating. Cos is also sine only, but just that you shift the graph. So this kind of waves which go up and down, they are called as sinusoidal waves. They are called as sinusoidal waves. So for sinusoidal waves, my dear students, where maybe this is the x-axis, this is your, wait, I just draw the wave randomly. Okay, so yes, this is your y-axis, this is your origin. Obviously the wave is going like this with some speed. This is a sinusoidal wave. There is some amplitude, of course. The equation will look something like this. Y is equal to a sine, either you can put kx plus minus omega t, depending on which side it is going. It could be either this side or that side. And usually you put some phi over here, which is a constant, because it's not necessary the wave exactly started from the origin. It started from the origin when time was 0. So maybe the wave had moved little bit ahead. Maybe the wave was here and maybe a part of that wave was partially passed on. So at time is equal to 0. That's why you have that phase constant, which was very similarly present in a simple harmonic motion in oscillations, if you remember correctly. Exactly. So understand over here, this entire thing is called as the phase of the wave. Phase of the wave. So therefore, when I say initial phase at the origin, that means time is 0 and x is 0. That initial phase at the origin, the initial phase, time is 0, x is 0, will be just phi. That is called as just simply the phase constant. Just simply it is called as the phase constant. Is that okay, everyone? And there is no hard and fast rule that you have to write the equation in this manner. There is no hard and fast rule. You can also write it in cos. You can also put omega t first, kx later. It's all okay as long as something x something omega t is present. As long as something x something omega t is present. So I will just mention it over here. All these are okay. All these forms are okay. What are those forms? Y is equal to a sine omega t plus minus kx. Y is equal to a sine kx plus minus omega t. Y is equal to a cos omega t plus minus kx. Y is equal to a cos kx plus minus omega t. All these forms are okay. Okay? Is that clear, my dear warriors? Everyone? Awesome. Awesome. Keep these things in mind. Keep these things in mind. Very good. Very good. What is A? A is amplitude. What is K? Angular wave number. What is omega? Angular frequency. What is phi? Initial phase or just the phase constant. So all these things are present over here. Okay, we have seen all these formulas. We have seen amplitude, we have seen period, frequency, angular wave number, phase, and all these symbols. All these symbols have been seen. Have you now got a feeling of what is a wave equation? Tell me now correctly, properly. All these symbols, are they clear? Y is your displacement. It depends on two things: equilibrium position x and the time at which instant you are looking. A is how much is the max displacement, that's amplitude. Omega is angular frequency. K is angular wave number per meter, how many radians. Phi is phase constant. Kx minus omega t plus phi is the total phase angle. Very good. Now, with regards to angular wave number and wavelength, remember I was just mentioning this to you. That if you take from one crest to the next crest, that becomes a wavelength. So one wavelength, one lambda corresponds to one complete wave, which corresponds to 2 pi radians. That's what we say. That corresponds to 2 pi radians. Now imagine I take two random points. They are separated by some distance delta x. This is x1, this is x2. Their separation horizontally, okay, their separation horizontally is delta x. Then for that delta x separation, what do you think is their phase difference? What do you think is their phase difference? When you go from one point to the other point, one wavelength, you go by a phase angle of 2 pi, so you get a different phase of 2 pi radians. You have covered 2 pi radians. So when you go by delta x, how much is the phase difference that you can expect? Unitary method. For this, it is this. For this, how much it is? That's all. So that delta phi will be 2 pi radians is per wavelength, so into delta x. This becomes your formula for finding that phase difference between any 2 points. So what is this formula for? This is the formula for the phase difference, between two points on a wave. Keep this in mind. Very good. Excellent. Okay, this is not yet part difference. I'm just saying that these are some random points. So think about it. For one wavelength, the phase was changing by 2 pi radians. So for one wavelength. So for delta x, how much will it change by? Radians per meter into meter. Meter got cancelled. What remained is only radians. Now are you getting it? So always remember, one circular motion, one wave, one oscillation, one wavelength, one time period always is 2 pi radians. And you always associate waves, oscillations to circles. Remember, that was the last lecture's end point, which we treat it like phasor. A phasor shows us, it represents an oscillation in a circular motion diagram. A particle going back and forth can be represented by circular motion, and the circular motions, different positions correspond to different points on that simple harmonic motion or oscillation. I hope you remember that. Pasu, go back from the start and watch it from the start. That will be better. Okay? Don't just start watching the lecture randomly somewhere from between. That will be of no use. There is one more thing over here which I would love to tell you. Imagine example, I tell you y is equal to 4 sine, alright, 2x minus 60 example. If I ask you wave speed, immediately you will be like, yes sir, it is omega by k. Omega is 6, k is 2. So you will be like, sir, it is 3 meters per second. Very good. But what if I ask you something called as the particle velocity, Vp? Understand the difference. Wave speed is along this direction. So if this is a wave like this, because there is a minus sign, that means it is going in this positive direction with a speed of 3 meters per second. That is the wave speed. But particle speed, particles are going up and down. They are performing SHM. Particles are performing SHM. So when you find particle speed, my dear students, it's basically differentiating the y coordinate with respect to time. Because understand, the particles are going up and down, up and down. They are just performing simple harmonic motion. So at any instant, if I know a particle is here at this y coordinate, so the velocity of that particle will be rate of change of the y coordinate, not x coordinate. So that will be derivative of the y coordinate with time. So 4 outside, just take the derivative of this 2x minus 60 over here. So when I take the derivative with time, x is assumed to be a constant. Oh sorry, I forgot the sign over there, my bad. Sine of 2x minus 60. X is assumed to be a constant, don't worry about it. What is the derivative of sine? It is cos. So cos 2x minus 60, and use chain rule and find the derivative of the inside term. Find the derivative of the inside term. What will that be? 2x is a constant, so 0, minus 60's derivative is minus 6. So it will be minus 24, 4 6 are 24, into cos 2x minus 60. That is what the particle's velocity will be. And do you see, it is definitely not a constant. It is definitely not a constant because the particle is going up and down, up and down. In fact, here the velocity of the particle will be 0 at the extreme. At this point, because it is at the mean, it will be maximum. It will be maximum at the mean position. Again, at this point, the velocity of the particle will be 0 at the extreme position. So it will perform SHM. The particles go up and down like SHM with varying speeds, but horizontally they are going with constant speed, which is the wave speed. These are two different things. Very good. Awesome. Thank you so much, Krishna, Niharika, for all that energy. Sarath, thank you so much. Keep lighting up the chat box. Thank you so much. And I hope you guys are, also liking the video and also subscribing to the channel. In case you haven't done that right now, do it. Okay. So keep all these parameters in mind. Very rarely a question on this might come, but if it comes, you should know how to do it by differentiating y with respect to time. That's how you get the particle velocity. So I'll just mention that probably over here, very rarely a question might come. Vp will be nothing but the derivative of y with respect to time, which is not going to be a constant, but velocity of the wave is f lambda, which is also omega by k, which is going to be a constant. These are two different things. Correct. Let's solve some questions coming up on your screen. Wave is given. Which numerical constants are in SI units? Okay. The calculate amplitude, wavelength, period of frequency, displacement, everything we have to find. Look at the equation, guys. Y is equal to how much is it? It's all in meters, right? So 0.005 sine 80x minus 3t. This is what the equation is. Compare it with y is equal to a sine kx minus omega t. If you compare it, immediately you will start getting the answers. Amplitude is 0.005 meters. You can also write it as 5 into 10 to the power minus 3 meters. So amplitude is 5 millimeters. Next, wavelength. For that we need k value. K value by comparison is 80, but k is nothing but 2 pi by lambda, that is 80. 2 cancels with 80, becomes 40. So this will become lambda is equal to pi by 40 of a meter. Right? Next, comparing, you get omega is equal to 3. That means 2 pi f is equal to 3. Right? That means f is equal to 3 by 2 pi, but this is in hertz. 3 by 2 pi in hertz. That is the next answer. Last answer. Find the displacement of the wave at x is 30 and time is 20. All you have to do is substitute the values over here. So it will be 0.005, and then you will have sine over here 80 into x. What is the value of x? X is basically 30 minus 3 into time. What is the time? That is basically 20. What will you get after solving? This is basically 5 millimeters into sine of, try this out, 8 3s are 24 and 8 into 30 centimeters. My bad. I have to keep this as 0.3 then. I have to keep this as 0.3 because this was 30 centimeters, and 3 into 20. Yes, that is also fine. 24 and 320, 60. So 60 and 24, my dear students, that's going to be 36 with minus sign, so minus 36. But how do you find sine of minus 36? Is it in degree? Is it in degree? Think about it carefully. It is not going to be in degree. It is not going to be in degree. This is technically in radian. Minus 36. This is all in radian. Whatever values you find, always it is in radian. So what you do, try to think of some trigonometric formula. Is 36 radian close to a multiple of pi or 2 pi? Because if it is close to 2 pi or pi is multiple, I can write it as 2 pi plus something, 3 pi plus something, or 2 pi minus something, or 4 pi minus something, which makes it much easier to solve. If you remember, 36, 3.14 is pi, so 12 3s are 36. So I think it is close to 12 pi. I think it is close to 12 pi. How many of you are able to visualize it? How many of you are able to visualize it? Yes, it is close to 12 pi. So why not write this as sine of minus 36 plus 12 pi. There is no harm. Sine theta is sine theta plus 2 pi. It's sine theta plus 4 pi. Sine theta plus 6 pi, 8 pi, 10 pi, 12 pi, 14 pi. Theta plus 2 pi, theta plus 4 pi, theta plus 6 pi, it's one and the same thing. 1 round, 2 rounds, 3 rounds, 5 rounds, doesn't matter. So this makes it easier. Now you can do the math. I think now you will get the answer in terms of radians, 5 millimeters. You multiply 12 with 3.14, you will get sine of some radians, and after that you can get the answer. I think that's what could have been done over here. Yes, 12 pi radian, you can see 12 pi radian is 37.71. 37 minus 36 is 37.71 minus 36 is 1.71 radian. So convert it into degrees and then you can find the answer. This happens in the logarithmic books. Otherwise, you cannot do this in the NEET exam. So if you are thinking from NEET perspective, this can't come. The answer will be left in this form only. Options will be like 5 sine minus 36, 5 sine minus 30, 5 sine minus 40. The answer will be left as options. You cannot obviously expect a NEET student to solve this without the use of log books or any other calculator. Deepanvita, we use 12 pi because I know 36 is very close to 12 pi. 12 threes are 36. So 12 into 3.14 is close to 36. So when I do that, what happens is I will be left with the sine of a very small angle. And whenever you have to find the sine of, okay, take the example of this. If you have to find the sine of 1000 degrees, what will you do? You will first think 1000 degrees means, or let's say even 750 degrees. Take this example, simple example. Okay, this is a very good example to help you out. When I say 750 degrees, when I have to find the sine of 750 degrees, okay, what will I do? I'll think, is it close to something? I think it is close to something. It is sine of 720 degrees plus 30 degrees. This 720 is a very special number. 720 is a very special number because this is 2 into 360. 2 into 360 plus 30. So basically you have covered 2 rounds. One round is 360 degrees. One round is 360 degrees. 2 rounds. And you are again traveling more 30 degrees. It's as good as saying just sine of 30 degrees, which is basically half. So whenever you have to find the sine or cos or tan of big angles, you try to convert it into a small angle. You take away that chunk which is just repeating, which is completely useless. That is usually the 2 pi, 4 pi, 6 pi part. You just take it away. That's all we have done. Got it? Everybody? Understood? Clear? What we have done? Okay. That's all I did over here. So I understood that, you know, this 36 radian is close to 12 pi radian. So it will be 12 pi plus or minus something. So I wrote it in that form, that 30 degree which I got in that problem, which I demonstrated, will be that small angle which I got over here, which is 1.71 radian. Cool. Great. Let's go to the next question, AIPMT. Why is y naught sine omega t minus kx? For what value of lambda is the maximum particle velocity equal to 2 times the wave velocity? Think about this. Think about this. How do we do this question? Here, observe carefully, there are 2 different velocities. Maximum particle velocity, Vp max, is equal to 2 times the wave velocity. 2 times the wave velocity. What is the formula for wave velocity? Omega by k. That is wave. That is always constant. Particle always performs SHM. In a SHM, what is the max velocity? What is the max velocity? Amplitude into omega. Amplitude into omega, yes or no? So can I just write amplitude into omega? Amplitude is y naught into omega. That's all. It's always amplitude into omega is your V max in a SHM. That's all. Omega cancels. So y naught is 2 by k. So k is nothing but 2 pi by lambda. 2 cancels. So y naught is a lambda by pi. Lambda is y naught into pi. Y naught into pi is A for Ames That's it. All India Institute of Medical Sciences is the answer. A for AIMS or AIPMT. Cool? Understood how to do these questions? These kind of questions can also come in your examination. Very good. Awesome. Awesome. Let's go. Let me just also drink water. Thank you for reminding me. All of you take a quick 1 minute water break. Let me also drink some water and come. Cool. All right. Let's move on to the next one, and that is speed of a wave. Now, this is so important because many teachers don't discuss this and many students also don't know this. Speed of a wave. I ask many students, what is the speed of a wave dependent on? And many students say that, sir, if frequency increases, then the wave speed will increase. If wavelength increases, then the wave speed increases. But then I ask students, okay, tell me one thing. If wave speed increases, then will the frequency increase or the wavelength increase? Tell me this. Let's see how many of you are able to answer this. If the wave speed increases, does the frequency increase or the wavelength increase? If you are able to answer this, I'm really proud of you. Well, I'll tell you what, there is a logic behind this. And if you know that logic, it becomes very simple. And the logic goes like this. We talk about a medium. A medium possesses two kinds of properties, if you remember. One is your elastic property and second one is your inertial property. Both these properties together, they decide the wave speed. They decide what? The wave speed, which is your V. Your source which is there, that source decides your frequency. The source, which is the speaker or somebody shaking that string, somebody pulling and pushing a spring, or somebody creating that wave on the sea, or a boat which is traveling, that disturbance, that decides the frequency F. And once these two get decided, this is decided, wave speed is decided by the medium, frequency is decided by the source, automatically in the end the wavelength gets decided. Automatically in the end the wavelength lambda gets decided. This is the correct flow chart. So my dear students, if I tell you V is equal to F lambda and I tell you, listen, the wave speed increased, maybe the medium changed. So who will change, frequency or lambda? Who will change, frequency or lambda? Frequency is dependent on the source. Speed increased means medium has changed, which has increased the speed. So automatically wavelength will increase. Frequency will remain unchanged. Similarly, if I tell V is equal to F lambda, I used only a new kind of source. I used a new speaker, new source, and the frequency reduced. So will wavelength change or wave speed change? Think about it. If I used a different speaker or a different source because of which the frequency reduced, great. Medium did not change. Still the medium around is the same. So wave speed will not change. But what will change indirectly is the wavelength. So wavelength will increase. Understood now? Lambda will change. So this is how you decide who will change. Understand, wavelength can't change first. Wavelength is always decided in the end. It's like if you have ever traveled with your family or extended family with lots of cousins when you were small, or maybe even now, and it's a big Innova like 7-seater or big Scorpio or XUV 700 or Safari kind of a car, what happens? First, the main member of the family will sit in the front beside the driver, or the person only will be driving. Then all your moms, everyone will sit in the middle row. All the chiller pillar go adjust in the end. You are never the priority. You are always going to adjust, go behind. Sometimes you will be put in the dicky also. So that is the same condition of wavelength. Understood? So the priority first comes to wave speed and frequency. In the end, adjusting nature is there with wavelength. How many of you did not know about this? Many coaching institutes do not teach that. Let me tell you. So now that we know frequency is decided by the source, wave speed is decided by the medium. So let's see what is the speed of a wave on a string. You take a string, stretch it, and you will see if there is some kind of a tension, the wave will be traveling with certain speed, and that string has a property called as, if you take 1 meter of length of the string, how much mass is there? That is lambda, which is the mass per unit length of the string, which is also dm by dx, or just mass per unit length. That is lambda. It is usually expressed in kgs, which is there per meter. Also remember, since lambda is mass per unit length, mass is density into volume. Volume is area of cross section into length. LL cancels, it will become rho A. So this is also a formula. You can use M by L or you can use rho A. Both of them are the correct formulas for finding lambda, which is useful for finding out the wave speed of that wave on the string. You take a string, create a wave, that wave will travel on that string, right? That is what it is. Okay, now what is that formula, you might ask? Well, Shreyas sir, please tell me the formula. Well, Shreyas sir tells the formula is nothing but elastic property. Elastic property is on the top, inertial property is below. Elasticity, elastic property, tension gives that elastic property. Inertial property, mass per unit length. That's all. That is the wave speed. Both the properties are there. So this is the wave speed on a string. Which is root of tension by mu. More tension, faster wave. Less tension, slack string, slowly it will go. Heavy string, mu is very large, denominator is very large. This ratio will reduce, wave will go very slowly. Light string, mu is very small, denominator is small, ratio will expand, will become big. Wave will go fast because the mass per unit length is small, easily it can travel. That's how this formula makes sense, logical sense. Is that clear, everyone? Everybody with me? Awesomeness. Very good. Let's move on to some questions. A wire of this long, mass, wire is under tension. What's the speed? This is NCERT exercise question. So let's try this out. V is root of, because it's a transverse wave on a wire rope string, I can use the formula root of T by mu, but mu is not given, length is given, mass is given, and tension is also given. So mu is mass per unit length, so L goes on the top. So now you just have to substitute all the values. Tension is 60, length is 0.72, mass is 5 into 10 to the power minus 3. 60 by 5 is basically 12. 0.72 I can write it as 72. 72 is 12 into 6 and 2 decimal places, 10 to the power minus 2, and this 10 to the power minus 3 is there. So this V will become, check this out, what will it become? 12 will come outside the root, root 6 will be there, 10 to the power minus 3 minus 2, right? So minus 1 will be there, so it will become root 60, root 60. So it will become 15 4s are 60. So root of 4 is 2. So 12 into 2 into root 15. So 24 root 15 meters per second. 24 root 15, if you find out the value, I think it will come out to be 93 meters per second approximately. Okay, so this will be approximately 93 meters per second. Root 15, you can think it is close to 4 because root 16 is 4. So root 15 will be 3.9 or something like that. So 4 you can take. So 24 4s are 96. So it will be slightly less than 96. So that's how you can mark and select the options without actually calculating. Moving on, next question. A string of certain mass, tension is given, length is given, some jerk is given to the string. How long does the disturbance take to reach the other end? Okay, so you have created a jerk and that wave is going to travel to this end of the string. How much time does it take? Well, the time is the length of the string divided by the speed. So what is the speed given by? The speed is given by root of tension by mu. Root of tension by mu. Is mu given? No. Mass is given and length is given. Okay, so I can also write this as L by root T and root mu is on the top. Okay, so L divided by root T. Root mu is mass per unit length. Root L will cancel. L will go on the top. Root L will go on the top. So this will become root of L into M divided by tension. So therefore, the value of the time that it is going to take, substitute all the values. What is the length? Length is 20 meters. What is the mass? It is 2.5 kg. What is the tension? That's 200, right? Can cancel this 0, this goes with this 10 times. So it will be 0.25's root, which is 0.5. So 0.5 seconds must be the answer. Yes, it is. 0.5 seconds it's going to take to go from here to here. Isn't it straightforward questions, guys? Shall we go ahead to the next one? Are you able to understand? These questions are very, very simple if you know the formula, which is root of tension by mu. So I think I use the symbol mu here while I discuss lambda. Actually, you can use mu also, you can use lambda also. It's one and the same thing. So while discussing here, I used lambda. You can also call it as mu or mass per unit length. This is same as lambda. Okay, don't get confused. Okay, I use lambda over here. You can also use mu, one and the same symbol, one and the same meaning. Cool. Let's move ahead. Speed of longitudinal wave. We saw speed of a transverse wave. Now we'll see the speed of a longitudinal wave. Now there are two gentlemen who gave this formula. The first gentleman was none other than your favorite. Who is your favorite? Who has been troubling you for 300-400 years? Yes, Newton. So Newton said that when sound travels, the temperature does not change and the temperature is almost a constant. That means it is isothermal process. That's what Newton said. But there was another scientist and his name was Laplace. Laplace said that when sound travels, then temperature is not constant. In fact, the variations, compression rarefactions happen so fast that hardly the gas gets any time to absorb or release heat to the other molecules. So there is no absorbing or releasing of heat. So the system maintains its heat content, meaning if Q is zero, no time at all, no time to exchange heat, that means it is an adiabatic process. Now you might be wondering, sir, why are we discussing isothermal adiabatic process? Well, let me tell you about it. See, the thing is, the speed of sound in a solid, right? In a solid is root of Young's modulus by density. What is it? Root of Young's modulus by density. So what is this Y? This is your elastic property, Young's modulus, which is your elastic property. What is this? This is your density. Which is mass per unit volume. Which kind of property does it represent? Inertial property, because mass is there. So this is the speed of sound if you are talking about solids. Like what is the speed of sound in stone, speed of sound in a metal, all of that. Have you heard when you visited some old fort or a palace, if you talk at this place, some other place can hear that voice? Have you heard about these stories? So, in olden times, they used to design forts and palaces in such a way that if somebody else is talking somewhere, that sound will nicely travel through that solid and it will reach somewhere else, and there the spies of the king or the king's trustworthy people used to listen. So if somebody talks somewhere else, then the king will get to know the information. Oh, these people are talking behind my back. Come here, come fast. And the king will be like, that's it. The person is dead next day. Yeah. So that's what used to happen in the olden days. The sound used to travel through the walls, which is nothing but solid. So if you know the Young's modulus and the density of those walls, you can find that speed. And usually it used to be really fast. Solids allow the speed to be really, really high for sound especially. Correct. Next is, if you are talking about liquids, speed of sound in liquids or basically gases. So it is root of, instead of Young's modulus, it is bulk modulus. That's the only difference. That's it. This is the bulk modulus. That's the only difference, my dear students. No other difference is there. So you can block this off. Okay. Sound can also travel in water. Remember that. If it is a gas also, you can use this. So not just liquids or even gas. Now what happens is, bulk modulus for liquids is known, but for gas, it depends on the process. If you assume the process to be isothermal, then the bulk modulus is the pressure itself. Bulk modulus is the pressure itself. But if you assume the process to be adiabatic, then thermodynamics says the bulk modulus is gamma times P, where this gamma is nothing but Cp by Cv ratio. Now what happened is, Newton one day he calculated the speed of sound. Okay, it is bulk modulus by density. According to Newton, bulk modulus is pressure, so upon density. He found the speed to be approximately 280 meters per second. This is what was calculated. This was what was calculated as per Newton's formula. Then actual speed of sound was measured. actual speed of sound was measured, and the actual speed of sound was found out to be close to 340 meters per second. Then people thought, what is this? Newton's formula is giving me 280 meters per second, actual speed is 340. Imagine if the situation back then was just like how it is in your practical laboratories in your school or colleges. Actual value which you should get is 25, but in experiment you get it as 12. Then what do you write in the conclusion? Why the errors? Why there is so much error? Why the difference? Lab error, instrument error, personal error, random error. So there were errors in the measurement. That's why instead of 25, I got 12. Okay, very good. You feel so proud that your value was not matching, and you wrote the explanation for that also. Haven't you got that satisfaction when you got different values and you write that personal error, random error, instrument error, that's why the readings did not match? Then a teacher can also say, no, oops, sorry, instead of giving 4 marks, oops, sorry, my hand just slipped and I don't know, I can't control, I just wrote -1. Teacher can also say that, no? Instead of giving like this, oops, sorry, my hand just slipped and it went like this. So my point is, my dear students, that this is not correct. What Newton calculated is obviously not correct. But if you use Laplace method, where you assume sound to travel without absorbing or releasing heat, that is adiabatic process, then the velocity, which is root bulk modulus by density, which is root of gamma p by rho, substituting the values, the velocity approximately came out to be 340 meters per second. Then people were like, oh my god, Laplace is correct. Laplace is correct. Personal error made, the teacher gives less marks. Sanvi, is that so? My teacher was very good in practical. I mean, in chemistry, though, very good. We used to burn the lab. Like random chemicals, we'll put in random chemicals and we'll randomly do some flame test. We'll randomly drop the matchbox in the dustbin and the dustbin will be on fire. So we used to do all these things. So, but in spite of that, the teacher was very nice. Teacher gave us full marks in that chemistry practicals. Physics, no. Gone. In spite of being a physics teacher, I used to get less marks because I was always mischievous, no? So every time one instrument will be broken because of me, you know? So I will be doing I will finish my experiment, but then I'll be doing some random things after the experiment is over. So teacher got scared of me and less marks for me. Anyways, so now you understand how Laplace formula works, right? So the correct formula for gas, then the correct formula for gas, let me go over here. So instead of this, I'll write a separate line over here. So if you want to find the speed of sound in gas, you better use gamma p by rho. Remember, p by rho, pressure by density, is nothing but RT by molecular weight. That is also a good way to write the speed of sound in a gas. Okay, gamma RT by m is also going to work, since we know ideal gas equation. For an ideal gas, Pm is equal to rho RT. So therefore P by rho is RT by m. That is the reason we can substitute P by rho as RT by m. Is that okay? Very good. Awesomeness. Yeah, Deepak, there are few things which were deleted, like your Doppler effect. Mainly the Doppler effect was deleted from this chapter, and you do not see intensity and energy related questions anymore. In fact, in NEET exam earlier, this formula was very popular, and that was the power, the average power of a wave on a string. wave on a string, there was a formula which was there. I'll still give it to you. The average power formula. This is half mu v a square omega square. Mu is mass per unit length, v is wave speed, a is amplitude, omega is angular frequency. This used to be the formula for the power which is going to be transmitted by the wave, but for a string. Similarly, there was average intensity, or just I can just call it as intensity of sound wave. Intensity of a sound wave. What is the difference between intensity and power? Power is expressed in joules per seconds or in watt. But intensity is joules per second per meter square, or just watts which is there per meter square. It is the energy per unit time per unit area. That is what intensity is. And that intensity of a sound wave comes out to be half the pressure variations amplitude square by 2 rho. You might be wondering, what the hell is this PM? What the hell is this PM, right? What is this PM? Let me tell you what this PM is. When you talk about sound waves, what is there? You will see that there is a compression, and then you also have rarefaction in between. So if one were to draw a graph of pressure with the distance, basically your x, pressure with the distance x, how will that graph exactly look like? If there was no sound in that air, then the pressure everywhere will be constant. This is without sound, without any sound. This is how the pressure will be everywhere. It will be same, and it will be the atmospheric pressure P naught. But now, if there is sound which is traveling, then what will happen? If there is sound which is traveling, then at compression, the pressure will be more. At rarefaction, the pressure will be less. So, you will see the pressure variations are somewhat like this. Something like this. More pressure, less pressure. More pressure, less pressure. This height which is there, this is PM. This is PM. This PM is called as the pressure amplitude. What is it called? This is called as the pressure amplitude. That's the max pressure, max variation of the pressure, max variation of pressure from the atmospheric pressure, max variation of the pressure from the normal or atmospheric pressure. Is this clear what is PM? Everybody with me? Yes, there are a lot of formulas. Very good, total joy. Now, there is one more formula over here. I'm just giving it to you for the sake of it. It may come, it may not come, because it is there from the deleted syllabus. Just giving it for the sake of it. See, if you focus on any particle, that particle goes back and forth. Let me just go behind. Probably you can see over here. Particle goes back and forth. Isn't there some displacement which is happening? Isn't each particle doing SHM? Isn't there displacement for each particle going back and forth? Displacement is happening, and more pressure, less pressure, more pressure, less pressure. So pressure is also there, displacement is also there. Pressure becomes high, pressure becomes low. Displacement increases, displacement decreases. Pressure reaches maximum value, pressure becomes zero. Similarly, displacement becomes maximum, displacement becomes zero, displacement becomes maximum, displacement becomes zero. So there is also another term called as SM, which is your displacement amplitude. Displacement amplitude. Keep this in mind. Very, very important. And both of them are actually related to each other. The pressure amplitude is bulk modulus into angular wave number into SM. In NCERT, you may not find it, but earlier it used to be there. Some questions used to be there. So I'm just giving that to you as bonus. That's all. PM is BKSM. Very easy to remember. Just say it. PM is BKSM. PM is BKSM. Prime Minister is BKSM. Prime Minister is BKSM. That's all. As simple as that. Understood? PM is BKSM. Okay. PM is maximum pressure amplitude. B is bulk modulus. K is the angular wave number. SM is maximum displacement of the particle. So if our particle is going back and forth like this, this is your simple harmonic motion of that particle. This will be your SM. This will be your SM, the maximum displacement. It's the amplitude of the SHM. Is that right, everyone? Great. Very good. Most of the syllabus, at least I would say 50% plus syllabus right now is done. Just in the Super 6 series, if you have been tuned on the channel from December, more than 50-60% high weightage topics. You take modern physics, logic gates, current electricity, you take about 1D kinematics, your basic maths, your units and dimensions, and so much more, ray optics, and then over here SHM, rotational mechanics. We are now into waves. Almost 50% weightage plus is done. Few more chapters also will be doing in the next few days, and you will see almost it will be done, my dear warriors. Yeah, very good, very good. Keep all these things in mind. Now let's see if we can do this question. Estimate the speed of sound at standard temperature and pressure. We are not interested in the calculations. We are just interested in the mechanism or the method of the problems. These are NCERT questions. 1 mole of air, mass is given, speed of sound is asked. So when, by the way, I think this question was for using Newton's formula, if I'm not wrong, using Newton's formula. So the speed of sound using Newton's formula is root of pressure by density, but pressure is not given and density is not given. Oh, but it is, oh, pressure is given. Standard temperature and pressure. Standard temperature and pressure means, I know the pressure will be basically 1 atmospheric pressure, which is 1.01 into 10 to the power 5. The problem is only with density. Density is mass per unit volume. The mass per unit volume is indirectly given. 1 mole is this many kgs. So think about it. 29 into mass is 29 into 10 to the power minus 3 kg. This was Pascal. What is the volume? 1 mole, remember, 1 mole of any gas at standard temperature and pressure is 22.4 liters, which is 22.4 into 10 to the power minus 3 meter cube. Oh, perfect. Just put it over here. 22.4 into 10 to the power minus 3 meter cube. That's it. Solve now. After this, nothing is remaining. Understood, my dear students? Yep. So solve this. You will get the answer as almost 280 meters per second. We'll get this as almost 280 meters per second. Logic is clear. Calculations, you can do it later on, but the substitution, how we are doing it, should be very, very clear. Awesome. Very good, Jivita. Okay, very good, Krishna. Very good, Total Joy. Come on, everybody keep answering the questions, okay? Moving on to the next one coming up on your screen. If you drop a stone, it falls into the water, it splashes the water, and you hear the sound after some time. What is the time delay when you hear the sound finally? So you are on the top of a tower and there is some water over here. You drop a stone. It falls down like this. It falls down like this, and then the sound which will come out from the water will take some time to reach on the top, right? This is how the sound will travel. Question is, how much is the time delay? Well, here is what I will say. The total time taken will be, first the stone has to fall. So the time taken by the stone for the free fall motion. some time will be there, which is given by the formula root of 2h by g, and the remaining will be the time taken by the sound to go up. So sound takes time of distance by speed. So distance by speed of the sound. Distance by speed of the sound. That's all. What is the distance? I think it is 300. What is the speed? I think it is 340. Then here, what is the root of 2h by g? H is 300. G is basically 10. 0, 0 cancels. 2 into 30, that's 60. 60 is 15 into 4. So it will be 2 root 15 plus this one. 0, 0 cancels. 30 by 2 is 15. 34 by 2 is 17. So that will be the total time taken. You can find it out by substituting the values. It comes out close to 8.7 seconds. This comes out close to 8.7 seconds if you find the values by substitution. Main thing is the method, nothing else. Main thing is the method. Very good, guys. Let's go now to the next one, which is going to come up on your screen, and that is your principle of superpositioning. Let's start with that. Ready for this? Ready for this? Okay, let's take a 2 minutes break. Let's take a 2 to 5 minutes break, and then we'll start off with principle of superpositioning. What say, guys? Let's start after 2 minutes. I'll just keep a timer. We'll come back. We'll take a short break and return. Okay, so we are back to the session. Let's continue with the lecture. And before the lecture, we completed what is the wave speed, and I told you the different formulas for string and sound. And I also told you about, energies. We discussed about energies as well. We spoke that energy formulas right now it's not seen in NCERT. But it's something which you should definitely have some idea about. Okay, that's what we have seen. Okay, so let's now talk about superpositioning of waves. What does this exactly mean? Now, when I say superposition, means both things are combined together to give you the total effect. Imagine you get very less marks in your mock test. Your teacher scolds you. Then on the way back, your friend is mocking you. Hey, see, I got nice marks. You are getting so low marks. When you reach home, your parents also are scolding you. All three effects will combine together and completely mess around with your head. It will demotivate you completely. It's not like, oh, teacher demotivated me and parents also demotivated me. My friends also demotivated me. These are not like selective. Okay, I'm just going to get demotivated by my friends. No, everybody will end up demotivating you collectively. All the effects are present together. So that's exactly what superpositioning of waves means. So what happens is, imagine one person is talking and the sound is traveling over here. The sound is traveling over here like this. The sound is traveling like this. There is another person over here. That person is also talking. The sound is going to travel like this. The sound is going to travel like this in this particular direction. So now do you see the sounds are going to meet in this particular place. The sounds are going to meet in this particular region. So I would say the sounds will interfere. Correct? These are your individual sources. This is your source 1. This is your source number 2. This is your source number 2. These two sources will produce individual sounds. They will interfere, and when they interfere, what happens is you will get a new sound only. You will get a new sound only. This is called as your resultant sound or resultant wave. And how do you find this resultant? How do you find this resultant? The answer for that is you take the sounds that will interfere, you superimpose them with the help of phasors, and that's how you get the resultant wave. You superimpose, you collectively add their each values, each effects together, you get their combined resultant effect or the resultant sound. That's what you will get. Hello Sarath, welcome back. Yes Krishna, the waves have started back. So that is the meaning of finding the resultant sound, and it happens via superimposing. How does superimposing exactly look like? Let me show you. Imagine there is some sound like this. Okay, there is some sound like this. And, or let me do one thing. This is equilibrium. There is one sound which is like this. And then there is other sound which is like this. Okay, so it's a big wave, something like this. Okay, this is also traveling like this. This is also traveling like this. Both these sources producing individual sounds, they meet, they add up, they superimpose. What I will get is the resultant. What I will get is the resultant. What I will get is basically the resultant. What I will get basically is the resultant. These two are basically your interfering sounds. Interfering sounds or interfering waves. Interfering waves, which are now superimposed. So how does that superimposed process looks like? So when you superimpose, you show both the waves at the same place. Meaning something like this. Show that one wave like this. Show that other wave like this. And show this other wave over here. Yeah, everybody with me? Like this. And now this is not yet complete. You are superimposing. Now the resultant will look something like this. The resultant will look something like this. You add both the effects. Here only one of the orange is present, so only orange wala wave is there. Till this point, you will see there is no yellow, only orange is there. After this, yellow is there, so the bump of that yellow will be visible over here. And after this point, the orange only is continuing like this. And here the yellow creates a dent in that. Yellow will create a dent in that like this till over here, and this continues. So this is your resultant wave. So this is basically how your resultant wave looks like. Isn't this crazy? So this is having both these effects together. You take each and every point, you add up each and every value, and you get the resultant. This is what a resultant wave looks like. Is that clear, my dear students? Everybody with me? Understood or clear or? Give me a thumbs up. Did you understand what is the meaning of superimposing? Superimposing, combining the effects to get a resultant. That's exactly what I told. They interfere, you superimpose, you get the resultant. Clear? Everyone? Awesome. Now, when you superimpose, you can have multiple kinds of interferences. One such example is when you have one sound like this of amplitude A1, other sound like this of amplitude A2. Okay, and what you are doing is you are adding both of them to get the resultant. In this case, you will see the crest, crest, trough, trough, crest, crest, trough, trough matching with each other. Such waves are then in phase. They are said to be in phase. They are said to be in phase. That means there is no lag between them. They are together. They are matching together. Crest matching with crest, trough matching with trough. In such a case, the resultant, my dear warriors, looks like this. The resultant looks like this. This is your resultant, and this resultant amplitude will be A1 plus A2. This is maximum value that you can get by adding two waves. Maximum amplitude you will get. Such kind is called as constructive interference. What is it called? Constructive interference. Is that very, very clear? Is that very, very clear, my dear warriors? Perfect. Perfect. So the crest and the crest add together to give you a bigger crest. The trough and the trough add together to give you a bigger trough. So the amplitudes will expand. Something like this over here. Let's say, let me just get rid of this. Okay, I will just maybe, I don't need this. Can I just copy this somewhere? No, maybe I'll just write it again. So y is, so instead of 4, let me make it 0.2. Okay, maybe it's fine now, 0.2. Okay, great, it looks good. It looks good. Let's look at this wave, nice and cozy. And here I will write it as 0.4. Then you will have cos, and then you will have, oops, my bad, cos, then you will have 3, and then t, and what is it, plus 9x, bracket complete. Okay, perfect. So this is one wave, the violet one. This is one wave, the blue one. Let me call this as y1. Let me call this as y2. And then let me write y is equal to y1 plus y2. Look at this. This is black in color, that one. I hope you can see that. Can I change the color? Maybe orange. Yes, perfect. Look at this. Y1 is this wave. Y2 is this wave. Both these waves, do you see their crests are matching with crest? Trough is matching with trough. Crest is matching with crest. Trough is matching with trough. When I add them together, what will I get? I will get a big wave. The orange one is the resultant wave. It is constructive interference. Constructive interference. Now did you understand? Priniti, is it clear? Yes, this is much sufficient, Athia, for your NEET 2024. Yes, and we'll be having more practice sessions in the future. This is your preliminary right from basics class. What if I create some kind of phase difference phi? I create some phase difference phi, and look at this now. My value of phi will be anywhere from your 0 to your pi. Pi is there somewhere. Pi is not there. Let me write pi. Yes, pi is there. And in steps of, let's say 0.1. Okay. Perfect. Let's see. Look at this. Is the value of phi 0? Yes, there is no phase difference. They are in the sync. They are in sync now. I hope you can see that very clearly. These waves, they are perfectly in sync. I slowly change this slider. See what happens. They went out of phase. Crest with trough, trough with crest. Crest with trough, trough with crest. Oh my God, if I add them together, I am going to get a much smaller, wave. Do you see that? I can change the amplitude as well to make things more clearer for all of you. See this. See this. I'm subtracting, or basically it's like, you know, when I add these two waves, because the crest and the troughs are together, what I'll get is the remainder. So the big minus that small one. Do you see that? And the moment I change this phase difference, I can see the resultant, which is that orange one, that guy's amplitude changes. If there is no phase difference, they are in sync, I'll get maximum amplitude. If I go to pi radians, which is 3.14, I will come to minimum. I will come to minimum resultant. Minimum resultant, maximum resultant. Minimum for destructive, maximum for constructive. Crest with crest, constructive. Crest with trough, destructive, which is least amplitude. Now are you able to understand constructive, destructive interference and their phase difference relationships? How many of you got it? Yes. Perfect. Perfect. Shruti, I would suggest you to concentrate on the class. Don't worry about when the class is going to end and when it is not going to end. That should not be the concern right now. Is there some more? Yes, there is definitely a lot more. Don't ask such questions. Okay. Now, over here, if I have to show destructive interference, this is how I will show it. Like, if one is amplitude A1 and the other one is amplitude A2, my dear students, then when I add them, but the crest and trough should not match. So the in fact, crest should not match with crest. Crest should be with trough. So it should be shown exactly opposite, something like this. See, crest with trough, trough with crest. This is perfect. Then when I show the resultant, my dear students, it will be something like this. It will be of a much smaller amplitude. This amplitude AR will be A1 minus A2. I don't know which one is big, so I'll put a modulus sign. This is said to be out of phase. This is said to be out of phase, and this is going to cause a destructive interference. This is going to cause a destructive interference. Is that clear, my dear warriors? Now, some of you will be like, sir, what if they are not in phase, they are not out of phase, it's something else only. If it is something else only, something like this. If there is one wave here having amplitude A1, another wave is slightly here having some another amplitude, okay, A2. They are not perfectly in sync, they are not completely out of phase, right? I hope you can see that. So there is some kind of phase difference between them. There is some kind of phase difference between them, and I will get maybe a new resultant wave. In this case, there is a phase difference of phi. Phase difference of, let's say, del phi. Then what you do is, you treat them like, you treat the phasors of the waves like vectors. Remember, any oscillating quantity has a phasor associated with it, a circular motion associated with it. So think of this oscillating wave phasor as a vector. You just randomly show A1 like this. The length should be equal to the amplitude. This guy you again probably show like this. This is amplitude A2. But you can see they are not in the same direction. There is a reason for that, because A1 and A2, they have A1 and A2, they have a phase difference between them. They have a phase difference between them. So their phasors, vectors, will have an angle difference between them. Now you add them vectorially. Meaning complete the parallelogram or complete the triangle, whichever method you want to use, you can use, and then show the resultant. Show the resultant using laws of parallelogram or laws of triangle. This will be the amplitude of the resultant wave. This will be the amplitude of the resultant wave. So AR bar technically is A1 bar plus A2 bar. This is what it is. Not just that, I can also say AR magnitude will be root of a1 square plus a2 square plus 2a1 a2 cos del phi. This is what it should be. This is what it should be. If you find the resultant amplitude. Is that okay? Everybody with me? Yes, perfect, perfect. Great. Yes, I think it should take another 45 minutes to 50 minutes, not more than that. Yeah. So keep all these pointers in mind regarding the interference of waves. So if it is constructive, amplitudes will be maximum. If it is destructive, then the resultant amplitude is minimum. If it is neither constructive nor destructive, it is something in between, then you find the resultant using the vector addition formula, whose vectors, the phasors should be treated like vectors. So I'll just mention it over here. The phasors of the waves have to be treated like vectors. That's how you get it. Phasors of the waves have to be treated like vectors to find their resultant. Is this point clear? Absolutely. Let me know in the chat box. From this you get reflection of waves and all of that. Let me just show that to you in a bit. But for now, can you solve this question? Can you solve this question? Because I feel after we solve this question, then we can go to reflection. It's going to be very interesting. Yep. Come on. x1 is a sin omega t plus phi 1, x2 is a sin omega t plus phi 2. If in the resultant wave the frequency and the amplitude remain equal to the amplitude of the waves, then the phase difference between them is how much, is the question. Okay. Now concentrate your attention on x1. For wave number 1, wave 1, what is the amplitude equal to? Amplitude 1 equal to, I think it is A. For wave number 2, what is that second wave's amplitude equal to? That is also A. What about the resultant wave? The wave which is resultant. The resultant wave's amplitude of that resultant, how much it is? The resultant wave amplitude is amplitude of those imposed waves, meaning it is also A. This is interesting. I add this wave and this wave, phasors treated like vectors. I get the resultant vector also as A, meaning if I show A1 bar plus A2 bar, I should get the resultant wave's amplitude. And I'm telling you that this and this all are equal. That means it should form an equilateral triangle. It should form an equilateral triangle. So this only way possible is A is like this A is like this, and the resultant A is like this. This is the only way possible using an equilateral triangle. Equilateral triangle. So a lot of people will say the angle is 60 degrees, so it should be pi by 3, but that is not the answer. That is what is the mistake many people do. See, when I taught you vectors, or you would have learned vectors, you would have seen that you never measure the angle between the vectors when they are joined head and tail. The tail of one vector is with the head of the other vector. You slide the vectors. You take this vector, slide it here till both their tails are joined together. So my dear warriors, now the angle will be 120 degrees. 120 is option B. That should be the correct answer. Yes, that is the correct answer. Understood? Clear? Everybody with me? Yes. It's me, Ahita. This lecture is going to lay your foundation for your NEET and boards as well, for your NEET 2024, irrespective of whether you're a fresher or dropper. And we are doing enough practice, but obviously after the class, it's your moral responsibility to solve many questions. Obviously, if you watch a video of how to ride a bicycle, you will not learn how to ride a bicycle. You will understand how to ride it, but The practice is very important. So you have to practice problems also on your own, although I'm doing enough practice over here. If some teacher, on some YouTube channel is telling you, whatever I teach in the class is enough, just watch my lecture and you are sorted in life, 100% that teacher is lying to you. They are making a fool out of you, that's all. They're just doing it for views, or they just want you to attend the class and make you feel that everything is being done. But at the end of the day, when you sit with the book and problems, you'll be like, oh my god, I'm not able to solve on my own, because you're just watching that class, you're not practicing. So watching is also important. Obviously you can't directly go and sit in front of the book, but you also need to give equal weightage for practice. Yeah, understood or clear? Very nice. What if I make a question like this? What if I make a question like this? Wave number 1 is 3 sine 4 pi t minus 7 pi x. Y2 is equal to 4 sine 4 pi t minus 7 pi x plus pi by 2. Then the resultant amplitude is how much? Resultant amplitude is how much? If you answer this within next 10 seconds, pat on your back, 700 plus guaranteed, just like the thumbnail says. Razina, I will be taking a special class tonight and I will be explaining what we are going to do this week. What do you think? What do you think, my dear students? Well, look at the equations. Both are waves. One of the wave has an amplitude of 3. Another wave has an amplitude of 4. The phase difference between them is 90 degree. One is having an amplitude of 3. Other is having an amplitude of 4. The phase difference between them is 90 degree. So what will their resultant amplitude be? Use Pythagoras. 3 square plus 4 square is root, which is root 25, which is just 5. That is the answer. Very straightforward. Wow, very good, Krishna, Sanvi, Madhu, Shivani, Rosina. Perfect. You guys got it, nailed it. That's what interference of waves is. It's vector addition. Many people do not know. It's vector addition. If you know vector addition, no, gone. Sorted for life. You know how to add waves. Now let's also go to reflection of waves. In fact, I would love you to see those reflection of waves rather than just showing the theory. So I'm just going to open up PhET. Yes, this is very nice. Just go to simulations, go to physics, and this is going to be very interesting. I just want sound and waves. And do we have sound and waves? Yes, perfect. I want waves on a string. Okay, so I open it up and let's see if it opens up. Yes, it opened up. Okay, let's go to no end. Look at this. I take this and make it go up and down. You can see nice waves are going. Interesting, right? Source decides the frequency. I move it up and down very fast, frequency increases. I move it up and down slowly, the frequency decreases. Source decides the frequency. Okay. If I reduce the tension, it will go very slowly. See this? How nicely slowly it is going because tension is low. Aram se, coolly it is going. I make the tension slightly higher, it will go little fast. I make the tension even higher, it will go very fast. Got it? What is this damping? Damping means energy is lost to the surroundings. There is some damping. If I take no damping, then all the energy will go. All the energy will go. The moment I make the damping lot, see how that energy is dying out. How the energy is dying out. See this? I'll make the tension low so that you can see it very clearly. Oops. See this. See how the energy is slowly decreasing by the time it goes. Why? Because the energy is lost to the surroundings. Is it clear? Is it clear how the energy is decreasing as it goes ahead? Right? Did you understand? Okay. Now, shall we do the main thing, whatever we had to do? Let's do the main thing, whatever we had to do. Okay. What we had to do? We will take fixed end. Fixed end means the other end is also held properly. The other end is also held properly. Nobody is allowing it to move. Let's create a crest and see what happens. See what happens to the crest. Okay, it's dying out very soon. Let's reset it, let's get it back. Reset it. Not so much of damping, little bit damping is okay. Okay. All right, let's see what happens. Oops, not so fast, not so fast. Let's do this. See what will happen. This is a crest which is going, crest which is going, crest which is going, went there, tubuk, came down as a trough, came down as a trough. This trough will come here, tubuk, went as a crest. So whenever you generate a crest from the fixed end, it will be reflected as a trough, and a trough will be reflected back as a crest. Is that very, very clear, my dear warriors? Is that very, very clear, my dear warriors? Let's try it once more. See how nicely it is going. Crest went and came back as a trough, right? And the trough will come back as a crest. What a nice thing. Perfect. Now let's get it back, and now let's make it as a loose end. Loose means it's like a ring on a pole or something, on a rod, and that ring can easily go up and down. There is no friction whatsoever. Let's remove that friction, right, and see what happens. Let's create a pulse. Yeah, just create a pulse. Wow. Oh, it came back as a crest. Okay, this was quite fast. Let's do it little bit slowly so that we can see it. Okay, crest, 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 crest. It went till there, came like this, but this is fixed, so I think it will go as trough. It will go as trough. Yeah, perfect, perfect, perfect. It is going till here. It is going till here. Big trough. Okay, it came back. That's how it works. Now this trough will again become crest, and again that crest will reflect it back as a crest. Is that clear? So after this visualization, I don't think you will ever be confused. So crest comes back as a trough from a fixed end. From a fixed end, a crest comes back as a trough, and trough comes back as a crest from a fixed end. But if it is a free end, crest comes back as a crest, trough comes back as a trough. These are some basic things which you should know. Shall we go ahead? Amazing. Yeah, after this, you will never ever forget. If you see, you will never forget. If you hear, you might forget. If you read, you will definitely forget. So you should see things, you should feel things, you should hear things. All your senses, use it. You should write it, practice. You should see, simulate, visualize, use your mind. Hear to the lectures. I won't say smell it, okay? That won't work. Don't ask, sir, should I also smell the books? Yeah, you can. You will look like a dog. Okay, cool. Let's move ahead now to standing waves. This is a very interesting topic. Very interesting topic. What is a standing wave? Who are these two on both sides? One is Pandu, one is Champa. Both are holding a rope, and they are physics students. They are my students. So they are going to communicate to each other using vibrations on the string, using some pulses on the string. They have their own language. Maybe Pandu sends a pulse like this, means I love you. Champa says this, means I love you too. Pandu only understands it. Understood? You will not understand, maybe Pandu, Champa understand. Then Pandu says, let's go for movie. This wave reaches here. This wave reaches here to Champa. Champa says, yes, let's go right now. This is that wave. So that wave reaches Pandu. Understood, my dear students, how they are communicating with each other? Not WhatsApp, not Snapchat, not Facebook, no Instagram. This is wave communication on string, which only Pandu, Champa understand. That's okay. That's okay. We are perfectly okay with that. Now, imagine Champa is not going to move. She's angry. They fought. What happens in a relationship is if they fight, usually it happens that that girl will be like, I'm not going to talk to you, nothing, no talking. She's going to be like a rigid end, So Pandu says I love you. Pandu says I love you. It goes like this. What will happen? That wave will get reflected back and it will come back to Pandu and it will keep going back and forth. It will keep going back and forth. Yes or no? Pandu realizes, oh my God, Champa is not replying to me. So Pandu says, I love you, 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 and it comes back to him. So now I love you, I love you, I love you is going there. From there it is getting reflected back. Pandu is keeping on saying I love you, I love you. It is coming back to him. Now you have two waves going in two different directions. One the actual incident and the other one is the reflected wave of the incident. These two waves are going in opposite directions, yes or no? These two waves are going in opposite directions, yes or no? What is one wave doing? One wave is taking energy from Pandu to Champa. The reflected wave from Champa to Pandu. Pandu to Champa, Champa to Pandu. One energy going here to here, another energy going from here to here. So where is the total energy going? Where is the total energy going? Is it going here or there? Pandu to Champa or Champa to Pandu? I feel it's going nowhere. It's stuck. It's stuck. It's stuck. Yes. So the energy is stuck now. Energy is neither going here nor it is going here. It is contained. Now what has been created is a standing wave. What has been created is a standing wave. Is that understood? So what exactly is a standing wave? When you have two waves of same energy going in opposite direction, two waves of same frequency, amplitude, obviously, in opposite directions. They are moving in opposite directions, and what they do? Obviously, they will interfere. And when they interfere with each other, you have to superimpose them. And you find the resultant. That resultant is nothing but a standing wave. In the first case, when both the waves were there, I would say the energy is flowing in opposite directions. And finally, what will happen when they interfere in that region, because it's standing, meaning that the energy is contained in a region. That's what will happen. Is that clear? Everybody with me till this point? Okay, perfect. So it so happens you can take two waves. Y is equal to a sin kx minus omega t. Y is equal to a sin kx plus omega t. Do you notice, my dear warriors, the amplitudes are same, but here it is minus, here it is plus. Minus means it is going this way, plus means it is going this way. Are these two waves going in the opposite direction, yes or no? Are you able to say that? Both these waves, same energy, same amplitude, but in opposite directions, same frequency also. So what will happen is when they interfere, that means you add this wave with this wave, with this wave. So you add this equation and you add this equation, you add these equations, what will you get? You add this equation and this equation, this equation and this equation. You can use sin C plus sin D rule and you get this. Sin C plus sin D rule says this: sin C plus sin of D is 2 sin C plus D by 2 sine C minus D by, sorry, not sine, cos C minus D by 2. So when you use that sine C plus sine D, which is sine C plus D by 2 and cos C minus D by 2, you get this particular equation. This is the resultant equation of the standing wave. It's not necessary you get sine cos every time, because if it was sine C plus sine, you will get sine cos. If it was sine plus cos or cos plus sine or cos plus cos, these terminologies will change. So in fact, I would say that the general equation of a standing wave looks something like this. Y is equal to 2a. It could be either sine or cos, does not matter, kx separately, into sine could be there or even cos could be there, does not matter, into omega t. See how this is different from your wave which goes from one point to the other. When a wave which goes from one point to the other, it was kx plus minus omega t. Both these terms were there in the same bracket. Here, this is there here, this is there here. They are there in different brackets. Understood? So that is how you identify whether it is standing wave or whether it is a traveling wave. Is this point clear? Is this point clear, my dear students? You should know this equation. You should know this equation. And what is this A, by the way? What is this A? This A is amplitude of any one wave, any one of the interfering waves, Now in this entire equation, if you notice, this is an equation or this is a part which is dependent on time. That means when are you seeing it? This part, if you see, is x. That means where are you seeing it? So we will separate where and when, and you will see a very interesting thing that happens. Where and when, and we will see a very, very interesting thing that happens. Let me just bring it over here. Observe this carefully. Y is equal to, say for example's sake, I write it 2a sine kx. I'm using sine, and then I use, cos omega t over here. This part is where, this part is when. This is when, and this is where, because there is x over there. If you just concentrate on this part, 2a sine kx, this is how it will look like. Observe carefully. A sine kx, it's a sine curve. It's a sine curve, and it is always, no matter when you look at it, it is always going to look like this. It's always going to look the same. Is that right? It's always going to look the same. Yes or no, my dear warriors? Perfect. But you know what will be different? When you multiply it with cos omega t. When time is 0, cos 0 is 1. That means maximum value. Meaning you multiply it with 1. You will get this. Because cos 0, this is at t is equal to 0. Cos 0 is 1, which is the max value that you can get. After some time, maybe omega t will become 90 degree. After some time, imagine when it becomes cos 90 is 0. So 0 into anything is 0. So the entire thing will run flat after some time. This is some time t1, right? This was basically t0. This is some time t1. After some time, omega t will become 90 degree or pi by 2. so it will become flat. After some more time, maybe it is T2, it will become cos of 180. Cos 180 is nothing but -1. Cos 180 is -1. So you multiply this with minus, meaning whatever you got here, it will be exactly opposite of it. It will be exactly opposite of it. You're multiplying it with -1. After some more time, let's say T3, it will be cos of 270 degree. Cos of 270 degree is basically 0. So anything into 0 is 0. It will become flat. It will become flat. And after some more time, T4, what will happen? It will become cos of 360, which is basically cos of 0, which is 1, which is as good as saying it is T0. It's back to this time. It's back to this same situation over here. It will come back over here. So if you combine all these things together, in one single place, it will look something like this. First it was here, then it was here, then it was here, then it was here, then it was here. After some time it might be here also. After some time it becomes flat, then it goes like this, then it goes like that, then it becomes like this, then it goes like this, then it goes like this. So do you see it is something like this? When you combine all of them at different times, at T1, T2, T3, T4, and again it will repeat its motion. Isn't that so? This is how a standing wave looks like. This is exactly how a standing wave looks like. If you don't believe me, it's okay. I will show that to you. I'll just show that to you right over here. Let's create a standing wave, my dear warriors. Let's restart this fixed end. Okay. Let's keep decent amount of tension. Decent tension. Okay, perfect. I can't keep in between. Okay. Anyways, let's try this out. See this. See this. Some parts are going up, some part is going down like this. This is like a standing wave. I hope you are able to visualize it. It's not so perfect. It's not the best standing wave, but yeah, some idea you are getting, right? Some parts are not moving, some part is going up and down, up and down. That is basically at different times. This is exactly a standing wave. Perfect, perfect. So this is how it looks like, going up and down. Once it is like this, then like this, then like this, then like this, then like this. So it is keeping on changing, right? So this is what you get. Some points are not moving at all. Some points are moving the most. So you will get the following. You will get the following. Each part is called as a lobe or a loop, and the length of it, because this is one wavelength, I hope you can see that this is one complete wavelength. This is one complete wavelength. So this is always lambda by 2. How much it is? If this is lambda, obviously this is lambda, then this is lambda by 2. Is that right? Some parts never move, like this one over here, this one over here, this one over here. They are called as nodes. What are they called as? Nodes. They don't move at all. But some points, they have maximum displacement. They have maximum displacement. They are called as antinodes. They are called as antinodes. Is that clear? Everyone with me? Everybody with me? Very good. Not just that. Observe one more thing. Whenever, okay, let me just create medium. Yeah. Observe one more thing. Whenever you are at the fixed end, what are you getting? What is this point or this point? What is this point or this point? What is it? Node or antinode? It's always going to be a node. What is it going to be? Node. Keep that in mind. But if you have a loose end, observe how it looks. Observe how it looks. See, what is that loose end going to be? Always the loose end is going to be antinode. Fixed end will be always a node. Fixed end is node, loose end is antinode. Are you able to see this? You can never ever forget it now. You can never ever forget it. Very good, very good, very good. So coming back over here. So whenever you have a fixed end, the end is fixed, or sometimes you have a pipe and that end is closed. So you will also see in case of sound also you can create standing waves. So you can have a pipe which is closed, then what you get is a node. Always what you get is a node. Keep that in mind. You'll always get a node over here. Is that very, very clear? Similarly, if you are at the free end, and another option is the pipe is open. It's an open pipe and you are creating a standing wave. In case of a pipe, flute, trumpet, waves get reflected back and forth. So you are seeing a open or a closed ended pipe. So either it is an open pipe or it is a loose end or free end. Then always what you get on the outer side over here is an antinode. Is what? An antinode. Is that clear, my dear warriors? Everybody with me? Everybody with me on this? Clear-o? Perfecto? Can we go ahead? Yes. Another important thing is, when I say this is a node or an antinode, okay, especially for pipes, this is for string, this is for pipes. There are two types of things which you can vary. One is pressure, one is displacement. If you remember, so longitudinal waves, the particles go back and forth, so there is displacement. The closeness of the particles decides the pressure. So am I referring to a node of pressure or node of displacement? Am I referring to antinode of pressure or antinode of displacement? That is something which you should be aware of. These nodes or antinodes are always the displacement nodes or antinodes. So in case of a pipe, on the closed side you have a displacement node, meaning the particles have nowhere to go. So it is having zero displacement, but pressure wise it will be an antinode. Maximum variations of the pressure happen at this part, so it is a pressure, it will be a pressure antinode. Keep that in mind at the closed end for a pipe. And here, because it is open to the atmosphere, the particles can go in and out, so there is maximum displacement, and the outside air will always try to make the pressure stable, meaning pressure variations will not be there. Because the air can easily flow in and out, it will stabilize the pressure, so variations are not there. So this will be a pressure node for a pipe. For string there is nothing like pressure and displacement, it's just displacement. Okay, only problem happens for pipes. Only problem happens for whom? Pipes. Is this point very, very clear? Pakka? Shall we go ahead? Shall we go ahead now? Pakka? Clearo? Okay, nodes and antinodes. You should know all these things. Now, main problems. All these things are there. Nodes and antinodes and wavelength and all of that. Now, a special problem happens again for pipes only. See, strings is very simple. Pipes only always cause that problem. If you have an open end, this is an open end of a pipe. Open end of the pipe. Open end always has a antinode displacement wise, meaning this should be like this, antinode should be formed. But what happens is, it is practically found that the antinode is not formed at the open end, it is formed slightly outside. It is formed slightly outside. This is what you will actually end up seeing. You will see that the antinode is formed slightly outside. This is where the displacement antinode or pressure node is formed. Because it is formed slightly outside, whenever you are measuring the length of that wave and all of that, you need to consider the fact that the antinode is slightly outside the open end. So there is an end correction. What is there? An end correction. There is an end correction. That end correction happens to be 0.3 times whatever is the diameter of the pipe. 0.3 times the diameter of the pipe is that end correction. We need to use that. So the antinode for an open-ended pipe is slightly outside. For closed end, there is no problem. For string, there is no correction. It's only the sound problems which cause that small problem over there. Keep all these things in mind. Okay, it is found to be slightly outside. See, I'm giving all the notes in a very systematic, proper manner. So when you download these notes, you'll get a link in the Telegram. If you're not a part of the Telegram, join the Telegram. You'll get a link. You can download these notes using those things. Okay, keep all these things in mind. Now, what are the different possibilities when both the sides are closed or both the sides are open, or one side is closed, one side is open, one side is fixed, one side is open, and all of that? See guys, I'll show you very simple way. Imagine you have a string and I tell you this side is free or it is open, and this side is fixed or it is closed. Even this side, it is closed or it is basically fixed. Both the sides are fixed. I hope you are able to see those lines. What are the different possible standing waves that you can get? We know one thing for sure. If it is a fixed end or a closed end, there must be a node on that side. Undoubtedly, non-negotiable. Everybody must agree to this. So, if I have both the sides fixed, meaning what I will have is a standing wave, probably either like this, right? This is a possibility, or even this is a possibility. See how the standing wave is changing like this. This is also a possibility, or even this is a possibility. Right? Or even this is a possibility. All these are possibilities. In each case, what is different? Here wavelength was huge. Wavelength is small, small, small. As wavelength reduces, frequency increases. So low frequency, high frequency, higher frequency, even higher frequency. Is that making sense to all of you? Is that making sense to all of you? Perfect. Now, if I ask you over here, every time do you see one complete lobe, two complete lobes, three complete lobes? In general, you have n lobes. In general, you have n lobes, and each lobe has a length of how much? I mentioned to you that over here. Where did I mention it to you? Somewhere I mentioned. I think here. Maybe here. Where did it go? I don't know where it went. Here. The length of a lobe is always lambda by 2. This is 1 lambda, so this is lambda by 2. Yes or no? So let's use that over here. Let's use that over here. this is n lambda by 2. So can I not say n times lambda by 2 is the length of that wire, is nothing but the length of that wire, or the length of the string, or the length of the pipe, whatever it is. Perfect. And what is lambda? What is lambda? Lambda is V by F. So that is L. So F will be NV by 2L. N times V by 2L. N times V by 2L. Is that right? Everyone with me? V is the speed of the sound or the wave. Length, whatever is given. N is some integer. F is the frequency. F is the frequency. So if I ask you over here, what is the value of N? Here the value of N, is 1. Here the value of N is 2. Here the value of N is 3. Here the value of N is 4. Very good. Here, what is the frequency? I will call it as F1. N is 1. So V by 2L. V by 2L. Here, that frequency F2 is 2V by 2L. 2 times V by 2L. Here, F3 is 3 times V by 2L. Here, F4 is 4 times V by 2L. 4 times V by 2L. Oh, V by 2L, V by 2L, V by 2L every time. So can I not see F2 technically is 2 times F1, F3 is 3 times F1, F4 is 4 times of F1. So can I not say Fn is n times of the first frequency, n times of the least frequency? Lesser than that, nothing is possible. Nth frequency is n times the first frequency. This F1 that you see, my dear students, this is called as the fundamental frequency. What is it called? Fundamental frequency. What is it called? Fundamental frequency. Keep this in mind. Very good. Very good. What is this called? N. This N. What is this N called? N is called as the mode. N is called as the mode, or in which mode it is vibrating, in which mode it is producing the standing wave. It is called as the mode, and this is the nth frequency. It's the frequency of that standing wave. Frequency of that standing wave. Sometimes you don't use that word mode and you call that N as harmonic. You call it as the harmonic. You call it as the harmonic number. Harmonic number. Meaning, for example, just look at it. If I tell you this is 30 Hertz, this is fundamental, and example I call F1 is 30 Hertz. Can you guess what F2 will be? It will be 2 into 30, that means it will be 60 Hertz. What will be F3? 3 into 30, that means it will be 90 Hertz. What will be F4? 4 into 30, that is 120 Hertz. What will be F5? 5 into 30, which is 150 Hertz. So if the fundamental frequency is 30 Hertz, every other frequency will be a multiple of it. So this will be then called as the first harmonic. This will be second multiple. This is a harmonic number, right? So this is the first harmonic. This is the second harmonic. This is the third harmonic. This is the fourth harmonic. This is the fifth harmonic, and so on and so forth. Like that. Is that clear, my dear warriors? Is that clear, my dear warriors? Very good, very good, very good. Proud of all of you. Yes. But there is also another name which is given to it, because the first harmonic is always the fundamental. It is also called as the fundamental mode, fundamental frequency, fundamental standing wave. Any number above the fundamental, over the fundamental, it's called overtone. Over the fundamental, overtone. This is the first time you are getting a standing wave after the fundamental. So this is the first overtone. This is the next one. This is called second overtone. This is the third overtone. This is the fourth overtone. That is how it works. That is how it works. Is this absolutely clear? How the naming comes? If you are still not clear, let me give you one more example. Let me give you one more example. Let's say we have 10 hertz. Let's say we have 20 hertz. Let's say we have 40 hertz. Let's say we have 70 hertz. Let's say we have 80 hertz. These are the frequencies of some random wave which is being produced. The least frequency is always the fundamental. Least frequency is always the fundamental. Keep that in mind. And the fundamental is also always the first harmonic. First harmonic. Now 20 is 2 times of 10. 20 is 2 times of 10. So that's why it is second harmonic. 40 is 4 times of 10. That's why it is not third, it is fourth harmonic. It is fourth harmonic. 70 is 7 times of 10. That's why it is seventh harmonic. 80 is 8 times of 10. That's why it is eighth harmonic. Is that clear, everyone? Very good. But if you look at overtone, after fundamental, this is the first frequency we are getting. So this is first overtone. This is second overtone. This is third overtone. This is fourth overtone, like that. Here this goes serially. Here this may or may not go serially. It depends on these values, which multiple it is in. That's how it is. Not many people know this. Not many people know this. Okay, so these are the different frequencies in which you can get it for fixed. Similarly, you can do it for fixed free and free also. Look at this. I have put it up on the table over here. Both sides free. Both sides free. You will have antinodes on the ends. Antinodes on the ends, and you might have some lobes in between. One fixed, one free, one closed, one open. Node, antinode, node, antinode, node, antinode, node, antinode, node, antinode. That's how you will get. There are formulas for this too, just like you had formulas for this one, just like you had formulas for this one. Here the formula was NV by 2L when both sides were closed, but when both sides are open, you will see the formula still remains the same. The formula is still going to be NV by 2L when both sides are open. Both sides are open. Number 2, you can also see all the harmonics are present. All the harmonics are present. Here, when one side is closed, one side is open, then the frequency becomes odd multiples of V, but by 4L. Be careful, not 2L, it is 4L. First harmonic, third harmonic, fifth harmonic, seventh harmonic, ninth harmonic, meaning only odd harmonics are present. Only odd harmonics are going to be present over here. Clear? Very good. I can see a lot of students getting their doubts clear. You should just know the formulas. Mainly you have got the understanding over here as well as over here. What is the meaning of node, antinode and all of that. And how the numbering happens. Later on, it's just the formulas. Odd V by 4L or NV by 2L. Don't remember the 2n minus 1 formula. That is very confusing. Don't do that. Don't do it by 2n minus 1, 2n plus 1. That is very, very confusing whether n goes from 1 or 2 or all. If you study the vibration of a pipe open at both the ends, then which of the following is not true? Which of the following is not true? Pipe open at both the ends. Pipe open at both the ends. First harmonic is there, second harmonic is there, third harmonic is there, fourth harmonic is also there. All the harmonics are present. Odd harmonics will be generated, yes. All harmonics will be generated, yes. See, even A is correct because it is not saying only odd harmonics. It's saying odd harmonics are there. Yes. If boys and girls are there in a class, then saying girls are present in the class, that is correct. Boys are present in the class, that is also correct. Only boys are there, that is wrong. Only girls are there, that is wrong. Boys and girls both are there, that is correct. Same way, odd harmonics are present. Yes, odd is present. Even is present, yes. Pressure change will be maximum, open end will be an antinode. Okay. See, whenever you have an open end, I have mentioned this before, open end is always an antinode. Antinode. It is an antinode of displacement. It is an antinode of displacement. Pressure change will be maximum? No. In fact, it will be a pressure node. Pressure node. So, pressure changes will not be maximum. In fact, it should be minimum. Minimum will be the correct one. Pressure node. Node means less variation. A lot of people make a mistake over there. Correcto? Perfect. Shall we go ahead, my dear warriors? Awesome. Come on. I want to see all your answers. If you guys got it. Next one coming up on your screen. A string is stretched between two fixed points separated by 75 centimeters. The two frequencies that we get consecutively, because there is no other frequency in between them. That means they are consecutive. The lowest frequency is how much? See, what they mean to say is, there is some fundamental frequency F1. After some time, you get 315 and the next frequency is 420. Nothing is there in between. And then you get the remaining frequencies. Obviously, 315 will be n times of F1. 420 will be n plus 1 times of F1. They are consecutive. There is nothing in between. N then n plus 1 directly. String fixed between 2 points. All the harmonics are present. If n is there, fifth is there, sixth will be there. 7 is there, 8 will be there. So n and n plus 1. So come on, what do you think is the lowest frequency? That is exactly the question. What is F1? What is the lowest frequency? F1 is the question. Come on, my dear students, it's so simple. You can see over here, 420 will be NF1 plus F1. NF1 is 315. NF1 is 315. So how much will be F1? It will be 420 minus 315, which is how much? 105. 105 is there as option number D. Just check this out. Yes, it is D option. Got it? D for doctor. Perfect. So if consecutive frequencies are present, then n will be there, then n plus 1 will be there. So obviously you can see now 315 will be 3 into 105. So this is the third harmonic. This will be 4 into 105. So fourth harmonic. So this is third harmonic. This is fourth harmonic. So they were consecutive. Next one. A steel rod is clamped in the middle. Fundamental frequency is given to be this much. What is the speed of sound in steel? This is also a very interesting question. This is an NCERT question. If you take a steel rod and you clamp it in between, then what will happen? That point is fixed, and that's why it will act like a node. It will act like a node, correct? Once it acts like a node, what kind of standing wave can you produce? I think like this. I think like this. It feels like this, right? See this kind of standing wave you can produce. What does it look like? It feels as if you have a pipe or a rod or a string and it is free at both ends. So isn't this like a rod which is free at both ends? Free at both ends, and it is at fundamental frequency, in the fundamental mode. In the fundamental mode or the fundamental frequency. Isn't it looking like that? And what is the formula for free ends, rod or string? The formula is NV by 12. Frequency is 2.53 kilohertz. So 10 to the power 3. Fundamental means 1. Speed, we have to find. Length, 100 centimeter, 1. So 2 into 1. So therefore, V will be 2 into 2.53 into 10 to the power 3. So how much will V come out to be? 5.06 into 10 to the power 3 meters per second. Let's see. Perfect. 5.06 into 10 to the power 3 meters per second. That's the speed. Did you understand it? Vinu, thank you very much for the idea. I will mint crores of rupees. Who told you all these things? Vinu? All these are random things which people tell. If I start my own channel, I will earn crores of rupees. I don't want all those things. I'm happy teaching here. I'm getting complete support from Vedantu. Vedantu is giving such nice material. It's giving such nice courses, right? It's giving you the best teachers at the back end. It's giving you test series. It's giving you notes. It's giving you material. It's giving you that offline experience. I'm happy this way. This is very good. In fact, you should have the best teachers in the best institute, in the right frame of mind, and who have a simple and a common goal, and that is the welfare of a below average student. At least a below average student should reach his destination. A topper student should use his full potential. An above average student should push himself and to become a topper. So that is what it should be. That is what your aim or any teacher's goal should be. And I feel that I am exactly aligned with this goal, right? So I'm happy this way over here. Yes. So moving on to the next few questions. A pipe open at both ends, which harmonic will it resonate at 1.1 kilohertz? Resonate means, it will be in sync. It is happy in that particular way in which it is oscillating. Will resonance be same with the same source be observed if one end is closed? Take the speed of the sound as this much. Okay, let's understand it. Open at both ends means the formula will be F is equal to NV by 2L. Source frequency is 1.1 kilohertz, so 1.1 into 10 to the power 3. N I don't know. Velocity 330. Length 30 centimeters, so this is 0.3. So N will be, this will become 1100. This will become into 2. I will do one thing. I will write this as 3 and I will write this as 3300. I shift the decimal here, I add 1 0. This 0, this 0 gone, this 0, this 0 gone. This 3 goes with this 33 11 times. Just check this out if N is coming out to be 2. Just check this out if N is coming out to be 2, my dear warriors. Everybody, how many of you got N is equal to 2? Very good, very good, very good. Now that means I got the first answer. In which harmonic mode? It's in the second harmonic. Second harmonic. We got the answer. Now for the second part. Will resonance with the same source be observed if one end of the pipe is closed? If you close one end, the formula will be F is equal to odd V by 4L. F is nothing but the same thing, 1100. Odd number, I don't know. Okay, V 330. 4 into length, 0.3. Just check this out. Are you getting any kind of value? Are you getting any kind of value of the odd number out here? If you solve this, this will become 1100 into 4 into 3 divided by 3300. Cancels. 3 into 11, 33. So I'm getting odd number as 4. Can odd number ever be 4? This is not possible. Not possible. Odd number, how can it be 4? Hence, will the resonance be observed? Definitely not. Definitely not. Got it? Did you understand how we came to the conclusion of this? Very good. So let's go to the next one coming up on your screen. Very nice question. A string of length L is fixed at both the sides second harmonic. Amplitude of the antinode is 5. The amplitude of a particle at L by 8 from the fixed end. What it says is, this antinode's amplitude is 5 millimeters. If you go at this point, which is L by 8, what is this amplitude going to be? That is the question. Now, if you go back to the equation of the standing waves long time back here, this part, if you notice, the 2a sine kx part, this part represents the amplitude at any point, 2a being the maximum amplitude. 2a being the maximum amplitude. Remember, this is basically going to be 2a. That's the maximum amplitude of an antinode, 100%. 2a into sine of 0 is 0, sine 90 is 1, so 2a into 1 is 2a. So that's the maximum possible value that you can get, and that is for an antinode. Now going back to this particular problem. Right over here, okay. If I want to find the amplitude at any location x, that will be nothing but amplitude of antinode into sine of kx into sine of kx. The amplitude of the antinode is 5. Sine of k is nothing but 2 pi by lambda into x. So that way I will get the amplitude of the particle at that location. So what is the value of x that I need to substitute? First of all, this is 5 sine 2 pi by something into x. What is that lambda? Oh, beautiful. Lambda is L itself. Can you see that? Right over here, you can see this is length L and this is exactly 1 lambda. So that is itself going to be L. What is x? X is given to be already L by 8. LL cancels, 2 8 cancels, becomes 4. So it becomes 5 sine pi by 4. Pi by 4 is 45. So it will be 5 by root 2 millimeters. 5 by root 2 millimeters is B for biology. There you go. So that's how some questions can come on the equation of standing wave also. Clear? Okay. Clear, everyone? Perfect. Perfect. So these are some amazing questions on standing waves, my dear students. Let's go to maybe some more questions that we have. Yes, over here. The fundamental frequency of an organ pipe of length 20 centimeter, which is closed, is equal to the second overtone of an organ pipe open at both ends. Length of the pipe open at both ends will be how much? Seems confusing, but let's go step by step. First part, fundamental of a closed pipe. Whenever they say closed pipe, understand it's not closed at both sides, it's closed on one side. So whenever they mention open pipe, it's not open on one side, it's open on both sides. So that's one common confusion which happens. So when they say closed pipe, it's closed on one side and open on the other side. Because if it is closed on both sides, then how will you hear outside? No, the sound will just go inside and out, and it will keep on getting reflected. Nothing will come out, so you can't hear anything. So that's why closed pipes are technically possible, but you don't use them in your musical instruments. Okay, so fundamental for a closed organ pipe means closed open side. The formula will be F is equal to odd times V but by 4L. Because it is fundamental, the odd number should be 1. So F will be V by 4L. That's the first one. Okay. Next, for this guy. For an organ pipe open at both sides, that too in the second overtone. Now, when you have an organ pipe open on both sides, the formula is NV but by 2L. And the N value can be 1, 2, 3, 4 like that. These are all harmonics. These are all harmonics. First harmonic is always the fundamental. This is first overtone. This is second overtone. This is third overtone. The question says second overtone. Second overtone means third harmonic. Second overtone means third harmonic. So the value of n is 3. So 3V by 2L2, that is what F is. The question is, if the fundamental frequency of the length is equal, clearly mentioned equal, that means this and this, they are equal. So this and this will be equal. That means V by 4L1 will be equal to 3V by 2 times of L2. Is that right? These both will be equal. 2 cancels with this 4 becomes 2. V cancels with this V. So L2 will be 3 into 2L1. So it will be 6 times of L1. Length 1 is 20 centimeters. So this will be 120 centimeters, which is option C. Which is option C. Yes, it is correct. Yes, it is correct. Got it, my dear warriors? So these complicated PYQs also you can solve if you solve it part by part and see what is the relation between them. That's all I'm doing. I'm not doing anything complicated. It's just that you have to slowly understand the problem part by part. So see how I'm solving. Trust me, you will be able to solve the problem in the same manner after the class also. Okay. Then there is another question like this. This also came in the previous years. There is a tube and it is resonating with a fork, tuning, not form, fork at some frequency. It is filled with water. Then to get resonance, again, the minimum length of the water column is. Okay. Let's understand the question. So there is a pipe. There is a pipe over here. This side is obviously open and this side is open. And there is maybe a tuning fork over here that is vibrating. That is vibrating with this, and you fill this with water. You fill this with water with till some height. Obviously, the water surface will act like a closed end. Will act like a closed end, and this is going to act like an open end. And you have filled the water. You have filled the water till some height, which is exactly what has been asked. And the original length of the pipe was given as 125 centimeters. Very nice. Question is, find that minimum length of the water column, that means height. For this to occur, resonance to occur, that means standing wave has to be formed. If standing wave is formed, that means this is something what you should get. Right? You should get something like this. Antinode and node over here. Closed end will have a node and the open end will have an antinode. This is what you should get. This is what you should get, right? That is what should happen. Perfect. Let's call that as the length, effective length. Okay, let's just call that as our effective length from here till here. Cool. So the frequency of the tuning fork will be odd multiples of V by 4L. Odd multiples V by 4L. So that L will be odd times V value is 330 divided by 4 times frequency. Frequency of the fork is also 330. So it will be odd number divided by 4 meters. Converted into centimeters, it will be 100 into odd number by 4 centimeters, which will be 25 into some odd number centimeters. So what are the different values of length which are possible? 25 centimeters, then 75 centimeters. Correct? Everybody with me? 25 is 125 centimeters and so on and so forth. These lengths are possible for here. But what do I want? Minimum water height. Minimum water height. So if this H has to be minimum, what will this length L be? If this has to be minimum, this L has to be maximum. But you can't say then I will make it 125 because you have poured some water. Don't use 125. The maximum possible value is 75. So the max value that you can get is 75 centimeters. So what is the height then? What is that minimum height then? If this is 75, so that will be 125 minus 75, which is 50 centimeters. So you have poured up the water till option A, which is 50 centimeters. Got it? This is how the question can be solved in a detailed manner. Yeah, I know 9 o'clock surprise, but hold on. My lecture is getting extended. I think I'll come up for the surprise at 10 o'clock now. Just give me some time. Yeah. Will come. I hope the session is not live. That would be funny then. Oh my god. 1 second. Let me just ask them to change the timing. Just 1 second. Okay, I've changed the timing. I've asked them. I think that it should reflect. Yeah, we'll come at 9:40. Okay, let me just complete the last part over here now, and that is beats. Everybody ready for the final thing, and that is beats. I'll just show you what beats is through this particular calculator. After that, you will never ever be confused. Okay, so remember, we had done this we had seen the superposition of two waves like this, superposition of two waves, right? Just some time back. Okay, y1 plus y2 was the resultant of these two waves. The original two waves were here and here. These were the two waves, and you add them together and you get the orange one, which is the resultant wave, correct? So now what we will do, let's just keep their amplitude same for the sake of simplicity. So let's say 0.2, 0.2. So this is how the resultant wave will look like. Now what I will do, I will just change the frequencies of both the waves, that's all. So maybe forget this also. Let me just keep it simple. 9x and 9x, both are 9x, similar functions. Now what I will do, instead of 9x, I will write it as 9.1x. 9.1x. Observe now. This is y1, which is 0.2 cos 9x. This is y2, which is 0.2 cos 9.1x. This wave and this wave, if you look at it separately, it looks same. If you put them together, also it feels almost same until you realize one small thing which is happening. Because this is 9x, 9.1x, they have different wavelengths or slightly different frequencies, and that mismatch is seen as you go ahead. Look at it. Initially both of them crest, crest, trough, trough, crest, crest, trough, trough all together. After some time, do you see their crests and troughs are in fact not matching. In fact, they are doing destructive interference. Do you see they are doing destructive interference? Crazy, right? Crazy, right? Everybody with me? Awesome. Let me put in some good amplitude so that you guys too can see it properly. Yeah, perfect. I think this was a bit too much. Maybe I can make it 0.8 and this also maybe 0.8. Perfect. And yeah, I think this should be fine. So initially they were together and then slowly the mismatch started. If I make it instead of that maybe 9.4 or something, now also you can see the same thing happening over here. Initially see both the waves start together, but slowly the mismatch starts to be seen and the crest and troughs are misaligned, and then again they start aligning themselves. Again they go off the phase, out of phase, crest with trough, trough with crest, and again after some time they match together. So if you have two waves whose frequencies or wavelengths are close to each other, you will see sometimes they will do constructive interference, sometimes they will do destructive, sometimes constructive, sometimes destructive, and this happens alternatively. This will happen alternatively, yes or no, my dear warriors? Perfect. And see how the resultant will look like. Wow, look at it, the orange one, guys. Constructive, big amplitude. Destructive, negligible amplitude. Constructive, very good amplitude. Destructive, negligible amplitude. So you will see this. This is basically called as beats, meaning loud sound, no sound, loud sound, no sound, loud sound, no sound, loud sound, no sound. So this is what is exactly beats. This is exactly what is beats. Okay, understood? So when, I think I have put it up over here, when two waves propagate in such a way that they interfere, they overlap, and their frequencies are very close to each other, then you get loud sound and less sound, loud sound and less sound, which is called as beats. You can see both the waves have very similar frequencies, 11 Hz and 9 Hz. 11 and 9 are very close, and you will see, you will get loud and low sound over here. Now the time from one loud to the next loud or no sound to the next no sound, that is called as the beat period. Beat period. Then delta F is called as the beat frequency, which is 1 by the beat period, and the formula for that comes out to be F1 minus F2 modulus. F1 minus F2 modulus. What is this F1? What is this F2? Individual waves frequency. If this is 11, this is 9, 11 minus 9 is 2. So the beat frequency is 2 Hz, meaning from one loud to the next loud, the frequency is 2 Hz, meaning in 1 second you hear it 2 times. This cycle happens 2 times. I hope this is very clear. NEET aspirant, I would just say, just follow this channel. Just go with the same flow. You will not be pressurized and you will not be relaxed. And very smoothly and conveniently will complete the entire thing. And you do self-study on the same things which we are doing here. That's it. Just follow the lecture plans over here. Everything will be sorted out. Till this point, everything is clear. Let's solve some questions then. Let's solve some questions. Two sitar strings, A and B, playing the note dha, are slightly out of tune and produce a frequency of 5 Hz. Produce a beat frequency of 5 Hz. Tension in the B string is slightly increased. The beat frequency is found to decrease by 3 Hz. What is the original frequency of B if A had a frequency of 427 Hz? A has a frequency of 427 Hz. Initially, what is happening is there is a beat frequency of 5 Hz. Beat frequency of 5 Hz initially, meaning B can have either how much? Plus 5. If you do plus 5, how much will you get? 427 432 hertz, or it can have 427 minus 5, which is 422 hertz. These are the two possibilities. This is also possible, this is also possible. 432 minus 427, 5. 427 minus 422 is also 5. The earlier beat frequency was 5 hertz. Okay. If B string's tension is slightly increased and the beat frequency decreases. Okay. So what happens when the tension is increased? What happens when the tension increases? Since V is root tension by mu, even wave speed increases, and frequency being NV by 2L, hence the frequency also increases. So if B's frequency is increased, what is found? That the beat frequency reduces to 3. So the new beat frequency is 3. That means there are two options possible, plus 3 and minus 3. If it is plus 3, 427 plus 3 is 430 hertz, and 427 minus 3 is 424 hertz. Tell me now, which one will be the actual frequency of B before? Just imagine if the older frequency was 432 hertz of B. If I make it 430, am I increasing the frequency or reducing the frequency? Obviously, I am reducing the frequency. Is that right? But here, from 422 to 424, here I am increasing the frequency. Here I am decreasing the frequency. It's given clearly that the tension is increasing, so frequency is increasing. So only this option can be possible. This can't be possible. This can't be possible. This can be possible, because here frequency is decreasing, here it is increasing. So the correct frequency of B must be 422 hertz. 422 hertz. Yes, you can see that. These kind of questions are very, very common, right? So usually beat problems usually come up with two solutions. There will be one extra data given to remove that data confusion, and then you can finalize either this or this. See, if I tell you, just imagine if I tell you something like this. You know what? I have a number in my mind which is 20, and the other number in my mind differs from this number by 3 units. The other number in my mind is differing by 3 units. So either it could be 17 or it could be 23. And I then tell you, hey, listen, that number which is there in my mind, if I increase that number, then the difference reduces. If I increase that number. So if I make that 23, 24, then what is happening? The difference is becoming 4. It's increasing. Here, if I make that 17 into 18, I'm increasing the number. Now the difference between 20 and 18 is becoming 2. That means it is decreasing. So what was that original number? It could be 17. It will not be 23. That's how you finalize the answer. Got it? How we have to conclude the final thing. So it's all about, playing out with numbers. You increase and decrease and see how it works. Let's take one more example so that you get it. This is a previous year question. A source of unknown frequency gives 4 when sounded with a known frequency. Okay, source of known frequency is 250. So this is 250 hertz. And the two possibilities that you can get, because 4 beats per second is given. So either plus 4 or minus 4. So 254 is possible, and even 246 is also possible. Both are possible. Yes or no, my dear warriors? Yes, perfect. Everybody with me? Awesome. Now read the next part of the question. The second harmonic of the source of unknown frequency, that means second harmonic means into 2. into 2. How much is this? How much is this? Come on, first find this out. 254 into 2, 246 into 2. How much will you get this as? How much will you get this as, my dear students? Come on, put up all the answers in the chat box quickly. How much will you get this as? Yes, you will get this as 492 hertz. You will get this as 508 hertz. Perfect. That is the second harmonic of the unknown frequency. This is unknown. Gives 5 beats per second with a source of 513. With a source of 513 hertz. 513. Oh, this minus this. Yes, the difference is 5 hertz. This with 513. Oh, definitely not 5 hertz. Definitely not 5 hertz. 492 and 513, definitely not 5 hertz. So that means this is out of question. This is the correct answer, which is 254 hertz. 254 is D for doctor. D for doctor. Got it? How we got it? You need to be a part of the Telegram channel. On the Telegram channel, by tomorrow, the PDF link will be shared. You can download that PDF by using that link. Okay, so on the PDF on the Telegram channel, you will get the PDF. There is one more question. I think I had kept it for homework. Just solve this. After solving the other 2 questions, this question will look very simple. I have completed the chapter. Let me tell you, I have completed the chapter. Whatever is there for NEET. In fact, I have given you something extra only. Now, make sure you are a part of the Telegram to get the latest updates, notifications, PDFs, quizzes, weekly mock test links, and much more. Link is there below. Be a part of it. Okay. And I want everybody who has watched this lecture till the end, you have to put the comment waved. So if you put the comment waved, I know that you have watched the lecture till the end. That's another way of marking your attendance apart from smashing the like button. Do that right now. Okay. Thank you so much. I'm pretty sure you enjoyed this lecture. You had a wonderful time, and plus you learned a lot. This chapter is completed. We did everything, be it speed, be it equation, be it even energy, superposition, interference of waves using vectors, even standing wave equations, organ pipes, waves on a string, nodes, antinodes, and beats. Doppler effect is not there in the syllabus as of now. So enjoy this lecture to the fullest. Watch this again if you want to get some more clarity as well. Okay. Bye bye. This is Captain Shreyas signing off. Hasta la vista.